Why we can't truly explore the ocean. Tonight, we're drifting beneath the surface into a realm that feels close to us, yet remains almost completely unfamiliar. The ocean blankets more than 70% of our planet, and still less than 5% of it has ever been carefully mapped. Everything beyond that is an immense blank, uncharted, unseen, and unexplored, despite satellites circling far overhead, despite our most sophisticated sonar systems and robotic probes. The majority of what exists below the waves remains unknown. In fact, we understand the surface of Mars more clearly than we understand the floor of our own oceans. To put that into perspective, only 3 people have ever descended to the Challenger Deep, the deepest point on Earth. That number is smaller than those who have walked on the Moon. And down there, the familiar rules of our world seem to fall apart. At just 1,000 meters, the final traces of sunlight disappear forever. Beyond that depth stretches a darkness so absolute that it has endured for millions of years. And yet, against all expectations, life flourishes there. Extraordinary organisms exist that challenge everything we once thought about how life should survive. Entire ecosystems are sustained not by sunlight, but by heat and chemicals rising from volcanic activity. With every descent into the depths, explorers return with living forms we have never encountered before. The ocean contains mysteries that quietly remind us how little we truly understand about our own planet. Most of the ocean is still waiting to be revealed. But the unsettling reality is that we may never be able to explore it all, not because we lack curiosity, but because of the immense obstacles involved. So why is it that we cannot explore the ocean in the way we imagine? What prevents us even in an era when we have built rockets and sent robots to distant planets? And why does the ocean, our own home, remain humanity's greatest unknown? Tonight we'll journey together into the ocean's dark side to examine what we know, what we don't, and why the sea may forever keep secrets beyond our reach. But before we begin, I'd truly love to know where in the world you're listening from and what time it is there. It's always remarkable to imagine these stories being heard beneath so many different skies. If you enjoy these calm journeys into Earth's hidden mysteries, please consider leaving a like and subscribing to the channel. And a heartfelt thank you to those of you who are already subscribed. You're helping this small corner of the internet continue to grow. I sincerely hope this story gently guides you toward rest. Now take a slow, deep breath, close your eyes, let your shoulders relax, and let's begin. When we lift our eyes toward the night sky, the stars seem unimaginably distant, and yet they feel oddly familiar to us. Using the lenses of telescopes, we are able to detect the faint light of galaxies that sit billions of light years away. We can follow the elegant shapes of swirling nebulae and calculate the dimensions of planets that circle stars far beyond our solar system. Space feels immense, yet it also feels accessible, as though its secrets are laid out before us, waiting to be gathered piece by piece. What is truly remarkable, however, is that our capacity to examine these remote realms often exceeds our ability to explore what exists beneath the rolling waves of our own oceans. The explanation begins with the fundamental behavior of light and water. Satellites drifting high above Earth can transmit radar signals across continents and deserts, charting mountain ranges and river systems with extraordinary precision. They can photograph the craters of the Moon and the deep canyons of Mars in astonishing detail. But when those same signals encounter the ocean, they quickly fail. Water absorbs light, bends radio waves, and scatters sound. To a satellite, the ocean becomes a glittering barrier concealing everything below its surface. What satellites can reliably measure is the height of the water itself. In certain regions, gentle rises and subtle dips in sea level betray the presence of ridges and trenches far beneath. These gravity-driven hints allow scientists to sketch a broad outline of the seafloor. This is how we know the general form of the Mariana Trench or the Mid-Atlantic Ridge, but the picture remains indistinct, more like observing the shadow of a mountain rather than the mountain itself. When astronomers rely on space telescopes, they are looking across distances so enormous that the figures almost lose their meaning. Light that has been traveling for billions of years still manages to reach our instruments. We can chart the structure of the universe across time, capturing images of galaxies as they appeared when Earth itself was young. By contrast, when oceanographers attempt to chart the deep sea, they encounter limitations after only a few short kilometers. Underwater sound replaces light as the primary tool. Sonar emits pulses that reflect off the sea floor, and by timing the return of those echoes, scientists can estimate depth and shape. Yet the ocean is vast, and sonar surveys must be carried out slowly, vessel by vessel, across immense expanses of water. Even then, sound weakens as it travels, and the deeper the ocean becomes, the more difficult it is to detect what lies below. The result is a collection of fragmented maps, narrow bands of clarity pieced together over many years, while most of the seabed remains unexplored. Now, consider Mars, a world tens of millions of kilometers away. Thanks to orbiting spacecraft, we possess high-resolution images of its surface. We can trace the paths of ancient rivers, measure the heights of extinct volcanoes, and observe the dust storms that sweep across its plains. Mars is dry, lifeless, and distant, yet we understand it more intimately than the dynamic oceans of our own planet. Earth's seabed, by comparison, is uneven and incomplete, like a canvas left mostly blank, marked only by a few scattered strokes. This contradiction lies at the center of the problem. Outer space, though far beyond ordinary reach, is transparent to our tools. The ocean, despite touching our shores and covering most of the planet, remains stubbornly opaque. Instruments that perform brilliantly in the cosmos struggle against the density and depth of water. Every technological advance seems to illuminate not only how far we have come, but also how much remains unfinished. Time itself also plays a role. A space probe circling a distant planet can collect terabytes of data in a single pass, surveying vast regions in a matter of days. Mapping the seabed with sonar, by contrast, is like painting with a fine brush on a canvas the size of Earth. It requires not days but decades, and still leaves most of the image empty. As a result, we occupy a peculiar position. We have charted the red deserts of Mars with striking clarity, yet we cannot say with certainty what lies beneath the waters just off our own coasts. We can study galaxies so ancient that their light began its journey before life on Earth existed, but we cannot confidently describe the creatures that swim only a few kilometers below the surface. It is this contrast that deepens the ocean's sense of mystery. The universe offers us a distant view, while the sea guards its secrets closely. What we possess are brief glimpses, silhouettes and fragments, suggestions of landscapes and life forms that remain hidden. And as we move from the question of what can be seen to the deeper realities of the ocean itself, we must confront obstacles rooted not only in the limits of our instruments, but in the very nature of the deep. Because beyond the challenge of mapping lies something far more formidable, the abyss itself, a realm defined by crushing pressure, numbing cold, and unending darkness. The farther one descends beneath the waves, the more the familiar laws of our everyday world begin to fall apart. What appears calm and peaceful at the surface conceals conditions so extreme that they push the boundaries of both human engineering and imagination. With every meter downward, another obstacle is added, until the ocean ceases to feel like water at all, and instead becomes an immense fortress guarded by pressure, cold, and darkness. The first of these defenses is pressure, an unseen weight that intensifies with every step into the depths. At the surface, we exist beneath the mild load of 1 atmosphere, the weight of the air above us. Yet for every 10 meters of depth, the ocean imposes an additional atmosphere of force. By the time one reaches 1,000 meters, the body is already enduring 100 times the pressure felt on land. To continue deeper is to confront forces so powerful they can crush steel and shatter glass. This is why deep-diving submarines bear little resemblance to the sleek craft of fiction. They are not elegant but spherical, because a sphere spreads pressure evenly across its surface. Their hulls are thicker than bank vaults forged from layers of steel and titanium. Even so, every descent carries danger, as the slightest flaw or fracture can lead to catastrophe. The Trieste, the first vessel to descend to the Challenger Deep in 1960, experienced a cracked window during its dive, a stark reminder that even the strongest designs remain vulnerable when faced with the immense weight of the deep. Pressure challenges more than machinery. It reshapes life itself. Creatures that inhabit the abyss possess cell membranes strengthened by specialized proteins and enzymes capable of enduring enormous force. Their bodies often lack air-filled spaces that could collapse under pressure. For them, pressure is not a threat, but a constant, the normal condition of existence. For humans, it stands as an almost impassable barrier separating our world from theirs. Cold forms the second barrier, advancing long before the deepest trenches are reached. Even at relatively modest depths beyond the reach of sunlight, water temperatures drop rapidly. Within a few hundred meters, the warmth of the surface gives way to an almost freezing chill, and the average temperature of the deep ocean remains just above 0 degrees Celsius. This persistent cold has shaped entire ecosystems. For humans, such temperatures can bring hypothermia within minutes. For machines, the cold slows electronics and stiffens lubricants, turning moving components fragile and unreliable. Life in these depths has adapted in remarkable ways. Many deep-sea animals operate with slow metabolisms, conserving energy in the cold. Some produce antifreeze-like proteins that prevent ice crystals from forming in their blood. Fish and invertebrates drift in near stillness, surviving through patience and efficiency rather than speed. The cold preserves the deep like a natural archive, allowing animal remains and shipwrecks to endure for centuries. For explorers, however, it means that every mission must rely on heating systems and insulation simply to keep equipment operational against the relentless freeze. Then comes the barrier that defines the abyss more than any other darkness. Sunlight, the great enabler of life, fades quickly in water. At a few hundred meters, only a dim blue glow remains. By 1,000 meters, the final ray disappears completely. Beyond this twilight zone stretches an eternal night that no human eye has ever truly adapted to. Here, the only illumination comes from life itself. Brief flashes of bioluminescence glowing in the black, or the momentary beam of an ROV's lamp sweeping across the seafloor. This darkness is more than a lack of light. It is a domain where evolution has taken unusual paths. Many deep-sea creatures possess eyes enormous in proportion to their bodies, designed to capture even the faintest glimmer. Others have lost eyes entirely, relying instead on vibrations or chemical traces. For humans, darkness removes all natural points of reference, leaving even the most advanced submersibles dependent on instruments rather than sight. The ocean floor here is revealed only by sonar pulses and the weak glow of artificial lights, never by natural vision. To confront all three barriers at once, pressure, cold, and darkness, demands engineering that approaches the limits of possibility. Every journey into the deep requires not only a vessel capable of surviving immense pressure, but also systems that can function in freezing temperatures and navigate a world without light. Even then, the ocean resists our efforts. Such voyages are rare, expensive, and brief, and for the most part the abyss remains untouched, a reminder that the sea does not surrender its secrets easily. Yet it is precisely these obstacles that grant the deep its enduring sense of mystery. Each time we attempt to descend even deeper, we are reminded not only of how unforgiving this environment truly is, but also of how extensively life has already adapted to survive within it. For every barrier that feels insurmountable to us, other organisms have discovered ways to endure, transforming the abyss into a place they can call home. And as the story of the ocean continues to unfold, another question inevitably arises. What kinds of landscapes remain concealed within these depths, the vast scars and trenches of earth that human beings have reached only a handful of times? Far below, the restless waves hidden from sunlight and cut off from the warmth of the surface. The seafloor suddenly falls away into enormous voids that slice deep into the planet's crust. These are the deep ocean trenches, among the most extreme and least explored environments on Earth. They are the marks left behind by tectonic forces, where one section of Earth's crust slides beneath another, driving rock downward into the mantle. The outcome is a wound on the planet's surface that stretches for hundreds of kilometers and plunges to depths greater than the height of mountains. The most well-known of these features is the Mariana Trench, resting quietly in the Pacific Ocean. At its deepest point, called Challenger Deep, the seabed sinks nearly 11 kilometers below the surface. To picture such depth, imagine Mount Everest, the tallest mountain on Earth flipped upside down and placed inside the trench. Even then, its summit would still lie buried beneath more than 2 kilometers of water. It is a realm so remote and so hostile that only a very small number of humans have ever witnessed it firsthand. The first attempt occurred in 1960, when the bathyscaphe Trieste carried Jacques Picard and Don Walsh down into the darkness. Their descent lasted almost 5 hours, as the small vessel groaned under unimaginable pressure. When they finally reached the bottom, they saw a flat plain of silt disturbed by their landing. Through a small porthole, they reported signs of life even there, tiny creatures moving through the gloom. After only 20 minutes, they began the long ascent back to the surface, leaving the seafloor as untouched as they had found it. More than 50 years would pass before another human returned to that depth. In 2012, filmmaker James Cameron descended alone in a specially built submersible. His craft, the Deep-Sea Challenger, was tall and narrow-engineered to endure the crushing forces of the trench. He spent hours exploring, collecting images and samples that revealed a stark yet hauntingly beautiful environment. Still, his dive, like those before it, covered only the smallest fraction of the trench, a single pinprick within an immense abyss. Since then, only a few additional descents have taken place, often carried out by experimental vehicles or privately funded missions. The total number of people who have visited Challenger Deep remains smaller than the number who have walked on the moon. Each descent represents a remarkable feat of engineering, requiring vessels with walls thicker than vault doors, systems capable of surviving freezing temperatures, and instruments designed to function in complete darkness. Yet the Mariana Trench is only one of many. There are more than 20 known deep-sea trenches across the globe, ranging from the Tonga Trench in the South Pacific to the Puerto Rico Trench in the Atlantic. Many of these are nearly as deep as the Mariana, but most are still unmapped and unexplored. They are enormous gashes in Earth's surface concealed beneath miles of water, containing landscapes as dramatic as the tallest mountain ranges. Steep cliffs, twisting valleys, and towering geological structures lie there unseen and untouched. Much of what we know about these trenches comes not from direct observation, but from remote instruments. Deep-towed sonar has hinted at strange formations, while robotic submersibles have captured fleeting images of otherworldly creatures drifting through the void. Amphipods as large as human hands, translucent snailfish, and microbial mats clinging to rocky walls have all been discovered in these depths. Yet every expedition seems to return with more questions than answers. The scale of what remains unseen is staggering, as if we are peering through a door opened only a fraction of an inch. These trenches are not merely biological frontiers, but geological ones as well. They define the boundaries of tectonic plates where Earth quietly reshapes itself. Earthquakes frequently ripple along these zones, and tsunamis are born in their shadows. Entire mountain ranges rise and collapse because of the slow grinding at their edges. Still, we lack detailed maps of these environments and a clear understanding of their hidden structures. For now, they persist like distant rumors, places that seem to belong as much to science fiction as to established science. And so, despite the fact that the ocean surrounds us, its deepest regions remain beyond our reach. We have only skimmed the surface of these vast abysses, barely brushing their edges, while their immense interiors continue to lie shrouded in mystery. With each year that passes, our tools and technologies become more advanced, yet the ocean trenches continue to remind us of how much remains beyond our understanding and how vulnerable our efforts are when set against the immense force of the sea. As we move further into this narrative, the lingering question is not merely what these vast wounds in Earth's crust look like, but what kinds of life exist inside them. In these shadowed depths of the planet, living organisms have somehow learned to persist against overwhelming odds, enduring environments that appear completely inhospitable, and it is toward these delicate and remarkable forms of life that our focus now shifts. For as long as humans have navigated the oceans, there have been murmurs of unusual creatures emerging from the deep. Sailors spoke of enormous tentacles as thick as tree trunks coiling around ships and dragging them down into the pitch-black waters below. For centuries, such accounts existed somewhere between terror and imagination, dismissed by many as pure legend. Yet in recent decades, we have discovered that reality was not as distant from these tales as once believed. The giant squid, long considered a figure of maritime myth, has been proven to exist not only in stories, but as a living, breathing animal with bodies extending beyond 12 meters and eyes larger than a human head. These creatures remind us that the ocean has always guarded its mysteries carefully. For most of human history, we never observed them alive. Our limited knowledge came from bodies washed onto shore or fragments pulled up accidentally in fishing nets. It was not until the early 21st century that cameras finally recorded a giant squid in its natural environment, moving silently through the dark waters of the deep. Even today, much of its life remains unknown, its habits concealed within the abyss. And the giant squid is far from unique. The deeper one descends, the more unfamiliar the ocean becomes, as if each layer represents a separate universe altogether. In the abyss, where sunlight has never penetrated, organisms have been compelled to evolve in ways that challenge our assumptions. Their bodies reflect the extremes of crushing pressure, intense cold, and eternal darkness. Many are translucent, their ghost-like shapes blending seamlessly into the surrounding water. Some species have developed the ability to generate their own light, becoming living beacons, used to attract prey, signal potential mates, or disorient predators. Others survive as slow-moving scavengers, carefully conserving energy in a realm where nourishment is rare, where the descent of a whale carcass from the surface can sustain entire ecosystems for decades. Every descent into these depths uncovers something unfamiliar. Remote-operated vehicles, or ROVs, have made it possible to explore the abyss far more frequently than humans ever could in person. Equipped with cameras, mechanical arms, and powerful lights, these machines descend into regions where pressure would destroy steel and temperatures would incapacitate most life forms. And with each mission, they return with images of creatures never before documented. Scientists estimate that most deep-sea species have yet to be discovered, their shapes still concealed within trench walls and along the fractured ridges of the ocean floor. It is as though the ocean is a book we have scarcely begun to read, with each page revealing another surprise. Some of these findings are both mesmerizing and unsettling: jellyfish, trailing tendrils that extend dozens of meters, drifting like galaxies beneath the waves. Fish with transparent heads and eyes that gaze upward through their own skulls, monitoring the faintest traces of light above. Shrimp adorned with glowing patterns that move together in synchronized displays, resembling living constellations. Yet for every extraordinary organism, we manage to observe countless others retreat into the darkness before we can examine them. The difficulty of studying these life forms means that our understanding is often incomplete. A fish captured on camera for only a few seconds may never be seen again. A specimen brought up from the depths may not survive long enough for us to comprehend its behavior or ecology. Entire biological communities flourish in conditions that feel utterly foreign to us. And the more we learn, the more questions arise. How do these creatures reproduce in complete darkness? How do they find their way through a silent world without visual markers or light? And perhaps most puzzling of all, how many species remain hidden in regions of the ocean that no machine has yet reached? It is humbling to recognize that even in an era of satellites and global communication, the largest habitat on Earth remains largely unexplored, still wrapped in a sense of legend. The ocean holds millions of years of evolutionary history, shaping forms and behaviors that no human has ever witnessed. Somewhere within the dark corridors of the trenches and across the vast plains of the abyss, there exist beings so unusual that they may redefine our understanding of what life itself can be. Every descent by an ROV, every brief and fragile window into the unknown, serves as a powerful reminder that our planet remains incompletely charted, incompletely classified, and incompletely understood. And as our journey continues ever deeper, it becomes increasingly apparent that the sounds, sights, and signals rising from the abyss carry mysteries just as profound as the creatures that inhabit it. The ocean is not a silent realm, and what we have detected from its depths is often as unsettling and evocative as the beings that drift through the darkness. Although the sea is frequently described as quiet, the reality beneath the surface is the opposite. Their sound reigns supreme. Waves crashing above, whales singing across vast distances, shrimp snapping with explosive force, and currents surging against the seafloor all blend together into a concealed symphony that fills the blackened waters. Unlike light, which disappears after only a few hundred meters, sound travels with astonishing efficiency through water. A low-frequency noise can move across entire oceans, guided along what scientists refer to as the sound channel, a deep layer where acoustic waves can propagate for thousands of kilometers with minimal loss of strength. Within this hidden highway of sound, some of the most perplexing signals ever recorded have emerged. One of the most famous is known simply as the bloop. It was detected during the summer of 1997 by hydrophones that had originally been deployed across the Pacific Ocean during the Cold War to monitor submarine activity. The sound defied expectations. It rose in pitch in a way that resembled the call of a living organism, and it was so powerful that sensors separated by more than 5,000 kilometers all registered it. At the time, no known animal could account for such a signal. Even blue whales, the loudest animals on Earth, do not produce sounds at that frequency, and the sheer intensity of the bloop seemed far beyond the capability of any recognized creature. For years, the mystery endured, fueling speculation that perhaps enormous beings lurked in the depths, unlike anything humanity had ever encountered. Later, many scientists proposed that the sound may have been generated by massive icebergs cracking and shifting, yet the legend of the bloop persists, because in the ocean, the boundary between explanation and enigma is never sharply defined. Not long afterward, another unusual signal was identified and given a name. It was called Julia, a long, sorrowful moan, recorded in 1999. The sound lasted nearly 15 seconds, reverberating across the Pacific. Some researchers suggested it too resulted from ice fracturing, but others could not ignore the unsettling sense that it resembled a cry, as if the ocean itself had exhaled in grief. What made Julia so compelling was not only its haunting character, but also the reminder that water's remarkable ability to transmit sound can easily conceal a signal's true origin. Julia, much like the bloop, left behind more questions than answers. Then came upsweep, the name assigned to a repeating sequence of sounds, first detected in 1991. Upsweep is characterized by long rising tones, reminiscent of the drawn-out note of an unfamiliar instrument. It has been recorded seasonally ever since, typically strongest during spring and autumn, yet its source remains unidentified. The regularity of its pattern suggests it is unlikely to be random noise. Some have proposed volcanic activity, since the region where it was detected lies along Pacific fault lines. Others suspect a biological origin, perhaps a rhythm of life that has not yet revealed itself to us. Upsweep continues to confound researchers, a signal without a clearly known sender. And there are many more such sounds scattered throughout decades of listening. Whistles, groans, bangs, and hums appear suddenly within hydrophone recordings and then disappear without warning. Some have eventually been linked to natural phenomena, such as undersea earthquakes, shifting ice, or the movement of powerful storms. Yet many remain unexplained. In the depths where crushing pressure dominates and light never penetrates, sound becomes the sole witness, carrying traces of events and entities we cannot see. These ghostly signals remind us of how little we truly understand about the ocean's interior. They also demonstrate the immense power of sound beneath the sea. On land, light defines our perception of space, but in the ocean, it is vibration, echo, and resonance that shape awareness. Whales rely on sound to locate one another across entire ocean basins. Submarines once depended on it for concealment and survival, and hydrophones installed to guard against conflict have instead offered humanity an unexpected window into mysteries no one foresaw. Each unexplained signal leaves behind a sense of wonder, because in a realm as vast and concealed as the sea, any sound could belong to something entirely unknown. The bloop. Julia Upsweep and countless others are not merely noises in the dark. They are reminders that the ocean is alive with voices, some familiar and others forever beyond our reach. And while the hydrophones continue to listen, the sea goes on whispering its secrets, drawing us deeper into its narrative, where new discoveries await with every descent. In the deepest reaches of the ocean, where sunlight vanished long ago and darkness extends without limit, there is still light born not from the sun, but from life itself. It glows in rhythmic pulses, shimmers in rolling waves, and sweeps across the bodies of organisms that appear as if they come from a different realm altogether. This phenomenon is bioluminescence, something so common and yet so enigmatic that researchers are only beginning to grasp its true breadth. Bioluminescence is far from uncommon in the ocean. In fact, it is believed that most deep-sea creatures possess some version of it. The light is produced by a chemical process within the body in which a compound known as luciferin reacts with oxygen, often activated by an enzyme called luciferase. This reaction releases energy as light, typically glowing in shades of blue and green that can travel long distances through seawater. For those who observe it, the sight feels almost magical, yet it is completely natural, refined by evolution over millions of years. The purposes of this living light are as diverse as the animals that create it. Some species use it to hunt. The anglerfish drifting through pitch-black waters suspends a luminous lure in front of its mouth. Smaller animals drawn in by curiosity or deception drift closer until the predator suddenly snaps its jaws shut. Others rely on bioluminescence for defense. When threatened, certain squid eject clouds of glowing ink, confusing attackers and buying precious seconds to flee. Some fish emit sudden brilliant flashes of light that startle predators and drive them away. Even tiny plankton, when disturbed by a passing boat, can glow in sweeping waves so intense they are visible from space, transforming vast areas of ocean into radiant blue fields. Communication is another hidden function of this light in the darkness. Where vision is limited, some animals use bioluminescence as a kind of language. Flashing patterns can signal readiness to mate, mark territory, or help individuals of the same species recognize one another. Certain deep-sea shrimp release rapid-coated bursts of light, while lanternfish display glowing patches on their bodies like identification tags. Every flicker and every shimmer carries meaning in the silent black depths. Perhaps the most haunting displays are those that seem almost purely artistic. Entire schools of fish ripple with light as they move like constellations sliding across the sea. Comb jellies, delicate as glass, scatter rainbows of iridescence across their bodies as they drift. At times, a single creature can resemble a floating galaxy with sparks of blue or green racing along its translucent form. These visions remind us just how alien the deep ocean can feel, even though it is a part of our own planet. What is especially striking is how much remains unknown. For many species, the precise reasons for their glow are still uncertain. Why would a tiny worm shine bright red in an environment where red light disappears almost instantly? Why do some jellyfish flash in patterns so intricate they appear intentionally designed? Each new discovery leads to more questions, and every expedition returns with fresh examples of life, illuminating the darkness in ways we never expected. The flexibility of bioluminescence is equally remarkable. It appears in organisms across nearly every branch of life, from microscopic bacteria to giant squid. This suggests that the ability to produce light evolved independently, many times each instance offering a solution to the challenges of darkness. It is not a single invention, but many, each shaped by its surroundings, each providing a different answer to survival in the abyss. The wonder of this light is not limited to the deepest parts of the sea. Even in shallow coastal waters on warm nights, swimmers can leave glowing trails with every movement as clouds of tiny plankton react to disturbance. Waves break into bright streaks along the shore, and the footprints of crabs can shine on the sand. These smaller spectacles echo the immense light show hidden far below, reminding us that the ocean holds far more secrets than we can see. To realize that in the absence of sunlight, life has created its own version of day, its own lanterns in the dark, is both humbling and astonishing. Bioluminescence transforms the deepest ocean into a shifting, glowing theater where survival, communication, and beauty unfold in silence. And as we move further into this story, it becomes clear that even stranger layers of the sea lie ahead, places where neither true day nor complete night exists, but something in between. Between the bright shallows and the eternal darkness of the deep is a region unlike any other on Earth. Scientists call it the mesopelagic zone, though it is more poetically known as the twilight zone. It extends from about 200 meters below the surface down to nearly 1,000. Here light does not disappear abruptly, but slowly fades into a dim, ghost-like glow. Sunlight filters down weakly, just enough to blur the edges of shadows, yet never strong enough to support the green of plants. It is a realm that is neither day nor night, a shifting boundary that shelters some of the most elusive life on the planet. The twilight zone spans an enormous region, wrapping around the planet like a concealed band of mystery, unseen from the surface above. Its scale is staggering, holding more living biomass than all of Earth's rainforests put together. In these dim waters move vast numbers of fish, squid, jellyfish, and drifting planktonic life, many species of which have never been collected or examined by science. Their bodies are shaped by darkness. Some possess smooth, silvery flanks that reflect the faint traces of light, allowing them to merge seamlessly with their surroundings. Others are deeply pigmented, nearly invisible, dissolving into the blackness below. Many carry their own sources of light, tiny sparks of bioluminescence that blink and shimmer like stars scattered across a fluid night sky. Each evening, as the sun sinks and darkness spreads across the ocean, the twilight zone erupts with the largest migration on Earth. Billions of fish and invertebrates rise from the depths toward the surface, in a movement so immense it appears from space as shifting shadows beneath the waves. During daylight hours, they remain concealed in deeper water, sheltered from predators. After nightfall, they ascend to feed on plankton near the surface, their glimmering bodies moving in harmony with the planet's daily rhythm. This journey, repeated endlessly, may involve more individual animals than all the herds and flocks roaming the land combined. And yet, for most of human history, no one was aware it was taking place. Life here is finely adapted to conditions that are both fragile and extreme. Many inhabitants have exceptionally large eyes, designed to gather the faintest glimmers of light, or upward-looking vision that detects the silhouettes of prey above them. Others rely on counter-illumination, producing light along their undersides to match the weak glow filtering down from the surface, erasing their outlines from view. Some species conserve energy by drifting slowly, barely moving in waters where food can be scarce. Then there are those that hunt using light itself, releasing brief flashes to attract prey, or to disorient it just long enough to attack. Despite its richness, the twilight zone remains largely unexplored. It lies too deep for satellites to observe directly, yet too shallow for most submersibles to remain for extended periods. Nets hauled up from these depths often damage or destroy the fragile animals they collect, leaving scientists with broken pieces instead of intact organisms. Cameras can only descend so far before pressure, cold, and darkness overpower them. Much of what we know comes from brief encounters, short expeditions, and faint shapes detected by sonar. In reality, only a small portion of this vast habitat has been studied. What limited knowledge we do have suggests that the twilight zone plays a vital role in maintaining the planet's balance. When its inhabitants rise at night to feed, they transport carbon with them, carrying it from surface waters back down into the depths when they descend by day. This vertical movement, repeated every 24 hours by billions of creatures, helps regulate Earth's climate. Yet, the true scale of this process remains unclear, largely because the animals responsible for it are still poorly known. To drift into the twilight zone is to enter a dreamlike realm poised between brightness and darkness, where the edges of life fade into shadow. It is a place of immense abundance, yet also of near invisibility, hidden just beyond the reach of human sight. And as we push deeper into the ocean's secrets, we uncover not only layers of water, but layers of life, each more astonishing than the last. In the late 1970s, a group of oceanographers lowered a submersible into the dark waters near the Galapagos Islands. Their objective was straightforward: to investigate a stretch of seafloor along a mid-ocean ridge where Earth's crust was slowly pulling apart. There were no expectations of anything remarkable. The deep ocean was believed to be lifeless, a barren desert, unable to support organisms without sunlight. But in 1977, when the submersible's lights revealed the seafloor, scientific understanding was forever changed. What they encountered were hydrothermal vents, cracks in the planet's crust, where seawater penetrates deep into hot rock, becomes superheated, and then erupts back into the ocean, carrying minerals and chemicals from far below. These vents resembled underwater chimneys, some towering like buildings, releasing dark plumes into the surrounding water. And clustered around them, to the scientists' astonishment, was life. Not a sparse scattering of organisms, but entire flourishing ecosystems gripping the edges of these black smokers, glowing gently in the beams of the submersible. Massive tube worms formed dense colonies, their red plumes waving in the currents. Clams as large as dinner plates coated the rocks. Unusual crabs scurried across the vent openings, and fish slipped in and out of the shimmering, heated water. It was nothing short of a revelation. A living community was present, thriving entirely without sunlight. For all of Earth's history, it had been assumed that photosynthesis lay at the heart of every ecosystem, that without the sun, no food web could exist. And yet in the overwhelming darkness of the deep ocean, life had discovered a different solution. The key was chemistry. Around these vents, bacteria harnessed hydrogen sulfide, a substance poisonous to most animals, and used it as their source of energy. Rather than relying on photosynthesis, which depends on light, they carried out chemosynthesis, producing sugars and sustaining themselves purely through chemical reactions. These microorganisms formed the base of the vent ecosystem, nourishing tube worms, clams, and countless other organisms that had evolved to flourish in this extreme setting. What once appeared to be a barren wasteland was actually a birthplace of richness, all driven by the heat rising from within the earth. The revelation of hydrothermal vents posed deep questions about how life began. If organisms could survive and even prosper here in total darkness and under pressures far beyond anything at the surface, then it is possible that the earliest life on Earth arose in similar environments. These vents supply more than just energy. They also offer protection, as mineral-rich chimneys create small enclosed habitats where molecules can collect and interact. Some researchers think these vent systems may represent the true cradle of biology, the place where simple chemical processes crossed a threshold into complexity and produced the first living cells. This idea extends even further. If Earth's oceans can support vibrant ecosystems without any sunlight, then perhaps other worlds can as well. Moons such as Europa and Enceladus, orbiting far from the sun, are thought to harbor liquid oceans beneath thick layers of ice. If hydrothermal vents exist on their ocean floors, as many models indicate, then life may not be unique to Earth. Chemosynthesis could be a universal strategy for survival in environments where light never penetrates. Each new journey to hydrothermal vent regions uncovers even more unusual adaptations. Tube worms, for instance, lack mouths and digestive systems entirely. Instead, they contain symbiotic bacteria within their bodies, enabling them to feed directly on the products of chemosynthesis. Vent shrimp possess light-sensitive areas on their backs that may sense the faint glow of superheated fluids shimmering through the darkness. Even the chimneys themselves, formed from minerals transported upward from beneath the crust, become delicate ecosystems, each one a towering structure of stone and life rising from the abyss. Despite their extraordinary richness, hydrothermal vents are fragile. The same mineral concentrations that make them so distinctive have drawn human attention, particularly from deep-sea mining interests. Metals such as copper, zinc, and even rare earth elements accumulate within the chimneys, tempting industries that view the deep ocean as a new frontier for extraction. Yet these ecosystems are young and vulnerable, sometimes existing for only a few decades before shifting or collapsing. Disrupting them could wipe out communities we barely understand and eliminate species that have yet to be discovered. Perhaps the most powerful lesson of hydrothermal vents is how they challenge the limits we once believed governed life. Without sunlight, without plants, and without the familiar rhythms of land and air, living systems do not merely persist, they thrive. They remind us that the mysteries of the ocean are not just about strange organisms or unreachable depths, but about the fundamental story of life itself. And as we descend further into that story, new layers of the sea are revealed, drawing us ever deeper into the unknown. When we shift our gaze beyond Earth past the swirling clouds and the blue arc of our oceans, we encounter other worlds that initially appear lifeless. Icy, airless moons circle giant planets, their surfaces locked in frozen stillness. Yet beneath those shells of ice, scientists now believe there are concealed oceans, enormous bodies of liquid water hidden in silence. Europa. Jupiter's luminous moon is one such world. Its icy surface is crisscrossed with fractures shaped by tides so intense that they warm its interior. Beneath those cracks lies an ocean that may exceed 100 kilometers in depth, holding more water than all of Earth's oceans combined. Enceladus, a smaller moon of Saturn, provides additional evidence. In 2005, the Cassini spacecraft passed nearby and detected geysers blasting from its south pole, jets of water vapor and ice particles spraying into space. These plumes originate from a global ocean beneath its crust heated by tidal friction, and the water contains salts and simple organic molecules, signs that chemistry is active in the darkness below. Then there is Titan, Saturn's largest moon, a world so unusual that it blurs the line between the familiar and the alien. On Titan, channels and shorelines carved by flowing methane and ethane, spread across the surface and below its frozen crust, scientists believe there is an ocean made of water blended with ammonia. What makes these findings so unsettling is how strongly they mirror our own planet. On Earth, deep beneath immense pressure and absolute darkness, hydrothermal vents release heat and minerals, forming environments where life flourishes without any sunlight at all. If similar settings exist on Europa or Enceladus, they too could sustain their own forms of ecosystems. Chemosynthesis, the same mechanism that supports life around our vents, may not be unique to Earth, but a widespread solution nature turns to again and again. The template already exists, concealed within our own seas. Yet if the oceans of our planet are still largely unknown to us, how can we expect to reveal what lies beneath the ice shells of distant moons? On Earth, we have only begun to explore the margins of the abyss. Every descent uncovers unfamiliar species, unseen terrains, and unanswered questions, despite the fact that these waters encircle us everywhere. Now consider the task of launching probes across hundreds of millions of kilometers, cutting through ice far thicker than any glacier on Earth, and lowering instruments into oceans we cannot directly observe. The difficulty is overwhelming, and yet the promise draws us forward with the same inevitability as gravity. When researchers investigate Earth's deep oceans, they are not only expanding our knowledge of this planet, they are also preparing for voyages beyond it. The unusual microbes that feed on chemicals rather than sunlight, the spectral fish drifting in the dim twilight zone, and the organisms that produce their own living light, all demonstrate what can survive in worlds isolated from a star's warmth. Each mission to a hydrothermal vent or an icy polar sea offers a preview of conditions that may exist on Europa or Titan. Our oceans become a living laboratory, the only reference we have for imagining life elsewhere. These otherworldly seas provoke questions that feel both scientific and profoundly human. Could life arise in places so distant from stellar heat? Would it resemble anything familiar, or would it take on forms entirely unlike those we know? If one day we send a submarine beneath Europa's icy shell, will it glide past glowing clouds of plankton-like organisms, or encounter nothing but bare rock, shaped only by currents? The answers remain concealed, waiting in waters that may have remained untouched for billions of years. The ambition to reach these oceans represents exploration at its boldest. It demands that we travel not just farther than ever before, but deeper than we have ever gone. Before we break through the ice of faraway moons, we must first learn to read the secrets of our own seas Because here on Earth the same narrative is unfolding quietly. What we uncover in our oceans does not belong solely to us. It may be the key to recognizing life when we eventually find it beyond our world. And so the enigmas of the deep ocean and the enigmas of the cosmos are intertwined reflections of the same enduring question. What does it mean for a planet or a moon to be alive beneath rolling waters, far beyond the reach of sunlight? The seafloor is not motionless. It is vibrant with fire. In these regions, Earth's crust is thin, cracked, and restless, allowing heat from the mantle to escape. More volcanoes are hidden beneath the oceans than exist across all the continents combined. Some estimates indicate that 3/4 of all volcanic activity on Earth takes place underwater, silent and unseen. These submerged volcanoes rise from the depths like mountains of molten stone, their flanks wrapped in darkness, their peaks sometimes reaching high enough to break the surface and create new islands. Along the mid-ocean ridges, where tectonic plates slowly drift apart, chains of volcanoes extend for tens of thousands of kilometers. These ridges trace the planet like immense scars, longer than any mountain range on land. Here magma rises from below the crust, forming new seafloor in a process that never truly ends. Each year, a thin sheet of fresh basalt spreads outward, and the continents shift almost imperceptibly, carried along by the restless mantle beneath. Seen from above, the ocean floor would resemble a gigantic zipper, slowly opening, releasing both fire and life into the depths. Underwater eruptions behave differently from those on land. When molten rock meets frigid seawater, it cools instantly, creating unusual rounded forms called pillow lavas. Plumes of superheated water and minerals surge upward, blending with the cold ocean and forming clouds that can rise hundreds of meters before dispersing. Sometimes these eruptions are minor, remaining hidden even from detection. At other times, they are immense, powerful enough to transform entire landscapes in darkness. When eruptions occur near coastlines or in shallow seas, they can send shock waves through the water, generating tsunamis that travel to distant shores. Because so many of these volcanoes lie buried beneath kilometers of water, studying them directly is extraordinarily difficult. The immense pressure destroys most instruments. Total darkness makes orientation and movement extremely challenging, and the intense heat near eruptions can ruin even the most sensitive equipment. Much of what scientists understand comes from indirect clues rather than direct observation. Seismic detectors registering distant tremors, satellites noticing subtle changes on the ocean's surface, or rare expeditions that unexpectedly encounter fresh lava flows. Each finding reinforces how much of Earth's geology remains concealed beneath unexplored and restless depths. One of the most striking examples occurred in the Pacific in 2009, when researchers examining the Lau Basin recorded images of an underwater eruption as it unfolded. Through the camera of a remotely operated vehicle, they observed jets of molten lava bursting into the sea, glowing bright orange, while the surrounding water erupted into white boiling clouds. It offered a rare view of creation as it happens, revealing the processes by which continents are formed and showing that Earth is still actively changing. These volcanoes are not solely agents of destruction. Along their slopes, life has adapted in remarkable ways. Hydrothermal vents, often linked to volcanic regions, release heat and chemical-rich fluids that support unusual ecosystems. Shrimp, crabs, and worms gather in enormous numbers, surviving by feeding on bacteria that convert chemical energy into nourishment. In an environment that seems utterly inhospitable, life thrives, demonstrating that some of Earth's most perilous landscapes can also be among its most productive. Still, the dangers cannot be ignored. When submarine volcanoes collapse or shift, they can trigger landslides that push aside massive volumes of water. Such abrupt movements may generate tsunamis even more destructive than those caused by earthquakes alone. The Indian Ocean tsunami of 2004, while primarily the result of a tectonic rupture, was influenced by underwater activity along the fault zone. It stands as a reminder that events on the seafloor can send powerful consequences across oceans, affecting distant shores and communities. What makes submarine volcanoes so difficult to study is also what gives them their aura of mystery. They exist in regions we seldom reach across terrains we have only barely charted. Each is a hidden mountain, a quiet architect of the planet, shaping coastlines and ocean basins beyond our awareness. As exploration pushes deeper, it becomes clear that the forces beneath the waves are not only molding Earth's surface, but also recording the planet's history in fire and stone across centuries. For generations, sailors told tales of enormous waves rising suddenly from calm seas, towering walls of water higher than any ship, striking without warning and swallowing entire vessels. These stories were passed down as sea lore and often dismissed by scientists on land as exaggerations, products of exhausted imaginations. For a long time, rogue waves were treated as legends, grouped with sea serpents and ghost ships. Yet in recent decades, the ocean has revealed that these unseen giants are real. In 1995, a massive wave slammed into an oil platform in the North Sea. Instruments measured its height at more than 85 feet, rising above the structure itself. The wave appeared suddenly vastly larger than the surrounding seas, and it closely matched descriptions sailors had shared for centuries. This marked the first time such an event was documented with precise measurements, forcing scientists to reconsider accounts they had long ignored. Since then, satellites monitoring the oceans have shown that rogue waves are not rare anomalies, but frequent travelers moving silently across the seas. A rogue wave can surge to more than 100 feet high, taller than a 10-story building. Unlike tsunamis, which result from earthquakes or landslides, rogue waves form abruptly in open water, often when smaller waves align perfectly, combining their energy until a single giant rises above the rest. Their existence may be brief, but their power is immense. A vessel caught in the path of one can be destroyed before any warning is sent, and some ships reported lost in calm conditions may have fallen victim to these sudden barriers of water. The enigma of rogue waves grows when considering how long they remained unverified. Despite countless eyewitness reports over centuries, solid proof did not emerge until modern radar systems and satellites could accurately record the sea surface. When scientists began studying this data, they identified dozens of such waves forming around the world each year. Some emerged in the South Atlantic, others across the Pacific, and many more in regions like the North Sea, where storms and currents intersect. It was never a myth, but a reality hiding in plain sight, too fast and too fleeting to leave clear traces. Yet rogue waves are not the only giants concealed by the ocean. Even more devastating are mega tsunamis, events so rare and violent that they resist comparison. Unlike conventional tsunamis, which already unleash staggering amounts of force, a mega tsunami can surge to heights exceeding 300 feet. These colossal waves are not born from the gradual movement of tectonic plates beneath the ocean floor. Instead, they arise from abrupt and massive shifts of water caused by extraordinary events. A gigantic landslide plunging into a narrow bay, the sudden collapse of a volcanic flank into the sea, or even the impact of an asteroid, can displace enormous volumes of water in an instant, creating waves that can loom higher than coastal mountains themselves. One dramatic example took place thousands of years ago in Alaska, when an immense landslide thundered into Lituya Bay. The resulting wave scoured the surrounding landscape, ripping trees from hillsides more than 1,500 feet above sea level, marking the highest wave ever documented on Earth. What makes this history so unsettling is the realization that the forces capable of producing such destruction have not disappeared. They remain part of the planet's active systems today. The Canary Islands in the Atlantic Ocean, with their steep and unstable volcanic slopes, have long been examined as potential sources of future megatsunamis. A major collapse there could in theory send enormous waves racing across the ocean, striking the eastern seaboard of North America with catastrophic consequences. While the probability of such an event occurring within our lifetimes may be low, the possibility still exists, serving as a sobering reminder that the ocean harbors powers far greater than even the most violent storms we commonly imagine. What links rogue waves and megatsunamis is their shared invisibility before impact. A seemingly tranquil sea can mask the buildup of immense energy gathering quietly beneath the surface until it suddenly focuses into a single towering wall of water. For those unfortunate enough to witness such an event firsthand, there is almost no warning, only the abrupt and terrifying sight of the ocean rising beyond the limits of imagination. These enormous forces, unseen until the instant they strike, remind us that the ocean is not only vast and mysterious, but also a realm where our sense of scale itself appears to break down. And just as the seas conceal these hidden giants of water, they also hide regions where life begins to disappear altogether. Places where the oxygen that sustains animals drains away, leaving behind silent expanses as lethal as any massive wave. Not all of the ocean's mysteries are buried in its deepest trenches. Some of the most disturbing are found much closer to the surface, in areas where life quietly fades. These regions are known as oxygen dead zones, enormous stretches of water in which oxygen levels fall so low that large animals cannot survive. Fish, crabs, and squid are forced to flee if they can, or they perish, leaving behind waters that feel disturbingly empty. What remains are only the smallest and toughest microbes, barely enduring in environments where oxygen has almost completely vanished. The ocean is normally alive with motion. Currents churn through its layers, storms agitate its surface, and waves continuously mix oxygen into the water. Yet in certain places, this delicate balance collapses. When nutrient-rich runoff from rivers pours into the sea, it fuels explosive blooms of algae. At first glance, the water may appear more vibrant than ever, thick with green plankton flourishing under sunlight. But when these algae die, they sink into deeper layers, where bacteria decompose them. That breakdown process consumes oxygen, steadily stripping it from the surrounding water until almost none remains. As oxygen disappears, larger animals suffocate, and the sea takes on an eerie stillness. Some of these dead zones grow to astonishing sizes. In the Gulf of Mexico, one such zone frequently expands each summer to cover an area comparable to that of entire countries. Similar regions have developed off the coasts of India, South America, and Africa, where rivers carry fertilizers and waste into the ocean. Climate change adds yet another layer of pressure. As surface waters warm, they become less likely to mix with the cooler layers below. Without this vertical mixing, oxygen cannot reach deeper waters, allowing suffocating conditions to spread even further. Year after year, these dead zones continue to expand, transforming once thriving ecosystems into ghostly underwater deserts. For explorers and scientists, these environments pose unusual and serious challenges. Submersibles and remotely operated vehicles depend on oxygen sensors and sensitive instruments, many of which struggle or fail in waters so severely depleted. The altered chemistry within dead zones can corrode metal, damage electronics, and reduce visibility, causing equipment that performs reliably in the open ocean to malfunction quickly. This makes studying these hostile regions even more difficult, as they resist both life and human intrusion. Even descending into such waters is deeply unsettling. Where vibrant ecosystems would normally flourish, there is instead an unnatural quiet, as if the ocean itself has been silenced. The few organisms that do persist here represent remarkable examples of adaptation. Certain microbes are able to survive without oxygen by using alternative chemical pathways, drawing energy from nitrogen, sulfur, or methane in environments where most life would instantly fail. Some environments release toxic byproducts, forming layers of water so extreme and inhospitable that almost nothing else can survive within them. These microbial communities may appear simple at first glance, yet they perform a vital function in shaping the chemical makeup of the ocean itself. They stand as reminders that life is resilient and persistent, finding ways to endure even when surrounding conditions collapse entirely. Still, what manages to survive in these places bears little resemblance to the richness and abundance found elsewhere, and the absence of fish or whales in these waters is profoundly noticeable. Dead zones, however, are not always permanent. Storms, shifting currents, or changes in temperature can disturb the layered waters and restore oxygen, allowing animals to return. But as climate change accelerates and human activity continues to pour nutrients into the seas, These suffocating regions are forming more frequently and lasting for longer periods of time. They signal a delicate balance being pushed too far, warnings that the ocean itself can lose its breath. To imagine the sea without its vast shoals of fish, without the quick flashes of squid, or the slow drifting movement of jellyfish is to imagine an ocean stripped of much of its wonder and voice. Yet these places do exist, spreading quietly beneath the surface. And as we move away from them into the broader ocean once again, we encounter other looming shadows not caused by a lack of oxygen, but by the presence of something that should never have reached these depths at all. Plastic has been carried into the deepest trenches on Earth. For a long time, the deep ocean was imagined as a realm beyond human influence, untouched by the noise and disorder of life on land. For centuries, it seemed impossible that anything created by human hands could travel such immense distances, slipping down into trenches and coming to rest on the seafloor miles below the surface. Yet, when scientists began deploying robotic explorers into the planet's deepest chasms, their discoveries were deeply unsettling. Even in the Mariana Trench, more than 10 kilometers beneath the waves, fragments of plastic were found. They appeared tangled within sediments suspended in the water column and even inside the bodies of animals collected from the abyss. These fragments are known as microplastics, tiny particles less than 5 millimeters across, often invisible to the naked eye. They form when larger plastic items such as bottles, bags, or fishing nets break apart under the combined forces of sunlight and waves. Carried by ocean currents, they drift across vast distances, sinking slowly until they spread across the deepest valleys of the planet. They are light enough to float for years, yet so enduring that they may never fully disappear. The very strength and durability that once made plastic so useful has transformed it into a haunting presence in every corner of the ocean. What makes this discovery especially striking is not only where the plastic has accumulated, but how it moves through living organisms. Deep-sea amphipods collected from the Mariana Trench were found to have ingested microplastic fibers, their translucent bodies threaded with materials that do not belong there. Mussels from coastal waters contain these particles embedded within their tissues. Fish brought up from mid-ocean depths reveal the same fragments inside their stomachs. Even plankton, the foundation of the marine food chain, have been observed consuming these particles, mistaking them for nourishment. This means plastic is not merely settling onto the seabed, but circulating through the very biological systems that sustain ocean life. The sheer scale of this problem is difficult to grasp. Scientists estimate that billions of tons of plastic have been produced since the mid-20th century, and a significant portion of it has found its way into the sea. Some of it gathers in enormous surface gyres, forming floating patches that extend for hundreds of kilometers, while far more sinks unseen into the depths. In certain locations, sediment cores drawn from the ocean floor reveal layers rich in plastic fibers, creating a new geological marker of our era. If future civilizations were ever to study these rocks, they would find the signature of our age written in polymers. Even the most remote and seemingly untouched waters are no longer free from this influence. Plastic particles have been detected in the Arctic and Antarctic, transported by winds and currents across entire hemispheres. They fall with rain, drift with snow, and settle into the ice that seals the polar seas. Each new discovery deepens an unsettling question. How can we hope to study the ocean as it truly is when we have already altered it so profoundly? For explorers and scientists, this contamination presents both a challenge and a paradox. Instruments lowered into the deep often return with samples that are already compromised, the smallest plastic fibers clinging invisibly to the water they collect. Even laboratories must work carefully to avoid introducing additional plastic into the very materials they are trying to analyze. The boundary between the natural and the artificial grows increasingly blurred, leaving us to wonder what the deep ocean looked like before our presence ever reached it. And still, despite the heavy burden of this understanding, there is resilience present as well. Life in the depths of the ocean persists, continuing to adapt in ways we have yet to fully comprehend. Scientists have identified certain microbes capable of breaking down specific forms of plastic, using them as a source of energy. These organisms, surviving and even thriving in the most unexpected environments, stand as a reminder of nature's remarkable ability to respond even to damage that appears irreversible. and yet the image remains vivid. The darkest regions on Earth, once believed to be beyond the reach of human influence, are now traced with strands of synthetic debris. As we move deeper into the story of the seas, a sobering realization takes hold. We are not only uncovering the ocean's secrets, we are also encountering a reflection of ourselves within it, a mirror scattered in fragments of plastic that have become woven into the very fabric of the deep. From this point, the ocean's narrative shifts once more toward the vast forces that shape the planet itself, the currents that influence climate and unite continents, the flowing pathways of water that transport warmth and sustain life across the world. Beneath the ever-moving surface of the sea, hidden from everyday sight, a slow yet immensely powerful current circulates water around the globe. It is commonly known as the ocean conveyor belt, a term that reflects both its steady motion and its profound significance. Unlike the waves visible to us or the tides that rise and fall with daily rhythm, this conveyor operates on timescales spanning centuries, transporting heat, salt, and nutrients across enormous distances. It links every ocean basin into a single global system, connecting the tropics with the poles and the sunlit surface with the darkest abyss. The journey begins in the warm waters near the equator. Here, sunlight heats the ocean and persistent winds drive surface waters in consistent directions, forming currents such as the Gulf Stream. This broad flow of warm water travels northward along the eastern coast of North America, carrying heat deep into the Atlantic Ocean. Along its path, it releases warmth into the atmosphere, moderating winters in Europe and shaping weather patterns across entire continents. Without this process, much of the northern hemisphere would experience far more severe cold, especially in regions farther north, such as the Labrador and Nordic seas. In these areas, the story takes a different turn. The warm surface waters cool, and as sea ice forms, salt is left behind, increasing the salinity of the remaining water. This water grows so dense and heavy that it sinks into the depths. This sinking action forms one of the driving engines of the conveyor belt, drawing additional warm water northward, while forcing cold water down into the abyss. From there, deep currents move southward, carrying cold temperatures and nutrients toward the Southern Ocean. Around Antarctica, these waters circulate and divide into pathways that eventually rise again in distant regions of the Pacific and Indian Oceans. The conveyor belt is not only a system of temperature regulation, it is also essential for distributing oxygen and nutrients throughout the ocean. As surface waters sink, they transport dissolved oxygen from the atmosphere into the deep sea. When these waters rise once more, they carry with them the remains of countless organisms that have drifted down from above, delivering nutrients that support new life at the surface. Through this continuous exchange, the conveyor weaves the ocean into a single ongoing cycle of renewal. Yet, this finely balanced system is vulnerable. Climate change poses a serious threat to the stability that keeps it functioning. As glaciers and ice sheets in Greenland and Antarctica melt, they release immense quantities of fresh water into the ocean. Fresh water is lighter than salty water, and when too much of it enters the northern seas, it reduces the salinity that allows water to become dense enough to sink. If this sinking process slows, the entire conveyor belt can weaken. Current studies already indicate that the Atlantic portion of this system is slowing, possibly reaching its weakest state in more than 1,000 years. The consequences of such a disruption would extend far beyond the ocean itself. Weather patterns on land are closely linked to the movement of the seas. A weakened Gulf Stream could bring harsher winters to parts of Europe, intensify hurricanes in the Atlantic, and alter monsoon systems that billions of people rely on for water and food. In regions such as South America and Africa, shifts in rainfall could threaten agriculture. Even the vast Amazon rainforest, one of the planet's vital lungs, depends on moisture transported by the ocean conveyor. Understanding these immense currents remains one of the greatest challenges in modern science. Satellites can track surface waters and measure temperatures, but the deep components of the conveyor are largely hidden from view. Instruments lowered into the abyss offer only brief glimpses scattered over long periods of time. The scale of the system is enormous. The forces involved are subtle and the time scale so extended that no single human lifetime can observe the entire cycle. In many ways, we chart the stars with greater precision than we map these slow-moving rivers of the deep. Yet their importance cannot be denied. They form the hidden framework of Earth's climate, the silent connections that bind weather ecosystems and life itself into one interconnected whole. As we move further into this narrative, the forces that sculpt climates guide us toward other concealed domains. Icy boundaries where even oceans lie trapped beneath frozen armor waiting to be revealed. At the far margins of our world exist zones where seawater merges with ice, frozen frontiers that feel stranger than anything familiar on Earth. The polar oceans wrapped in cold and quiet extend beneath skies, washed in pale light or swallowed by unending darkness. Their surfaces are sealed by wandering plates of ice, yet below them, life persists in concealed waters that remain among the least explored regions on Earth. These environments are at once delicate and vast places where the distinction between sea and land dissolves into frozen terrains that resist simple description. Antarctica stands at the center of this enigma. Beneath its immense ice sheets, some reaching depths of more than 4 kilometers, rest hidden lakes that have been cut off from the atmosphere for millions of years. Among the most extraordinary of these is Lake Vostok. Larger than Lake Ontario, it lies beneath a massive ceiling of ice that has kept it isolated since long before humans walked the Earth. Its waters have never felt the brush of wind or the touch of sunlight. Pressure from the ice above keeps the lake liquid, while geothermal heat rising from Earth's interior provides a faint internal warmth within this concealed world. Scientists believe that entirely unique ecosystems could exist there, microbial life forms adapted to conditions unlike anything we know. Reaching it, however, presents an extraordinary challenge. Drilling through kilometers of ice carries risks of contamination, and so Lake Vostok remains largely untouched, perceived only through samples of refrozen water, lifted in ice cores, faint hints of a vast living body still hidden from direct contact. The ocean encircling Antarctica tells a story of its own. Here the Southern Ocean flows around the continent in a current so immense and powerful that it links all the world's oceans together. It is the only current that travels continuously around the entire planet, uninterrupted by land serving as a global highway for nutrients and life. These waters are frigid, dense, and rich in oxygen. They sink into the deep ocean and drive the great conveyor belt that helps regulate Earth's climate. The life that inhabits these seas is molded by extremes. Colossal squid roam the depths. Penguins plunge into icy surf. Tiny krill gather in numbers so vast that they are considered among the most important species on Earth, sustaining whales, seals, and countless fish. Without the polar oceans, the pulse of the entire marine system would weaken. The Arctic, though smaller in scale, is no less mesmerizing. Here, sea ice expands and contracts with the seasons, covering millions of square kilometers during winter before retreating in summer. This ice is far more than frozen water. It is a living structure that shelters algae and plankton, clinging to its underside, forming the base of entire food chains. Polar bears hunt along its margins, seals surface through its cracks to breathe, and narwhals and belugas weave their way through its shifting maze. Beneath the ice, the Arctic Ocean conceals basins and ridges that remain only sparsely mapped regions so remote that only a handful of scientific expeditions have ever reached them. The vulnerability of this environment is striking. Rising temperatures cause the ice to melt earlier each year, thinning the cover that has defined the Arctic for millennia. As the ice withdraws, the delicate balance of life that depends upon it is profoundly disturbed. Exploring these frozen oceans ranks among the most demanding challenges science has ever faced. Technology must withstand crushing cold moving ice and isolation that can last for months at a time. Submarines risk becoming trapped beneath solid ice sheets. Instruments freeze, batteries fail, and storms sever lines of communication. Even satellites struggle to observe these regions, their signals scattered by snow and cloud. As a result, much of what we understand about polar oceans comes from fragments of information assembled like brief glimpses through thick fog. What has been discovered is remarkable, yet it is evident that we have barely scratched the surface. And while Antarctica's buried lakes and the Arctic's drifting fields of ice continue to resist complete exploration, they remind us of something deeply significant. These frozen frontiers are not empty wastelands. They are living laboratories. Within them, Earth's secrets are stored in silence. Locked beneath the ice are records of climate stretching back millions of years, preserved in layers of snow that capture every storm, every temperature shift, every breath of carbon dioxide. Encased within the waters are life forms that may teach us how survival persists in the harshest conditions, and perhaps even how life could exist on distant frozen moons. From this point, the story of the ocean flows outward once more toward the smallest inhabitants of the deep microbes that flourish where light and warmth never reach, carrying us into an unseen realm that reshapes our understanding of what life can be. Far below the waves, in a domain that appears hostile to any living thing, a hidden kingdom endures. It is not governed by whales or colossal squids, nor by the fish and corals visible to the naked eye. This realm belongs instead to the smallest residents of all microscopic organisms that thrive in environments once believed to be utterly uninhabitable. Their domain is not defined by forests or reefs, but by individual cells that attach themselves to rock, float with the currents, or flourish within chemical plumes rising from the ocean floor. At hydrothermal vents where dark clouds of superheated water billow into the sea, temperatures can exceed 300 degrees Celsius. In these extreme conditions, rather than perishing in the intense heat, microbes have adapted to turn these vents into places of life. They do not rely on sunlight, which never reaches such depths, but instead draw energy from chemicals released from within Earth itself. Hydrogen sulfide, deadly to most living things, becomes their primary fuel. Through these chemical processes, entire biological communities take shape. Tubeworms, clams, and shrimp cluster around the vents, living in close association with microbes that convert toxic substances into usable energy. What begins as life too small to see becomes the base of ecosystems as complex and productive as tropical rainforests, all existing without any sunlight. In other regions of the ocean, methane seeps slowly escape from sediments on the seafloor, releasing gas that rises gradually into the water above. For most organisms, methane offers no nourishment at all. Yet certain microbes have evolved the ability to use this gas as an energy source. By doing so, they create pockets of life in places that would otherwise be nothing more than lifeless mud. Mussels and other animals establish themselves in these areas, relying entirely on their microbial partners for survival. This capacity to transform gas into food reveals a level of biological creativity that goes far beyond our everyday expectations. Some microbes push these boundaries even further, consuming materials that seem almost impossible to imagine as nourishment. There are bacteria that feed on oil, breaking down slicks that spill into the ocean. Others have been discovered attached to metal surfaces, slowly extracting energy from iron and manganese. Some are even able to digest plastics, a capability so recent and unexpected that scientists suspect these microbes are evolving in direct response to human pollution. Across the ocean, no matter how harsh or hostile the conditions may seem, there appears to be some form of life prepared to adapt and persist. The significance of these microbial realms far outweighs their minute size. They do far more than merely survive in extreme environments. They actively shape the chemistry of the entire ocean. They recycle nutrients, filter harmful substances, and even influence the gases that eventually enter the atmosphere. Without their constant activity, the balance of the planet itself would begin to break down. And yet, our understanding of them remains remarkably limited. We have explored only a tiny fraction of these organisms. Every deep-sea expedition brings back microbial samples that have never been observed before. Many of these microbes cannot be cultivated in laboratories, disappearing once they are removed from the darkness and immense pressure of their natural habitats. Their mystery remains inseparable from the deep ocean itself. What makes these microbes even more extraordinary is the potential they hold. Some produce compounds that could be used as antibiotics or treatments for cancer. Others create enzymes that may help break down plastic waste or unlock new sources of renewable energy. Within their microscopic forms may lie solutions to some of humanity's most pressing problems. But there is another side to this story. Microbes can also pose risks. Some thrive on toxins that could be dangerous if released, while others might alter environments in ways we do not yet understand. The deep sea contains both opportunity and uncertainty, and within its microbial kingdoms are secrets we are only beginning to uncover. The story of these microbes reminds us that the creativity of life exceeds our own imagination. While we look to the skies for signs of life on distant worlds, vast microscopic universes already exist beneath our feet, hidden in darkness and waiting to be discovered. From these concealed realms, the ocean draws us toward deeper questions where history itself is preserved in shifting sands and layered sediments, holding memories of Earth that reach back to the very beginning of time. The ocean does more than conceal unfamiliar creatures and landscapes. It also preserves the forgotten chapters of human history. Beneath its surface rest remnants of our own past, sealed in silence for centuries and sometimes for thousands of years. Countless shipwrecks lie scattered across the seafloor, their wooden hulls and iron frames slowly eroded by salt and time. Some vessels carried wealth, others carried people, and every one of them carried a story. Each wreck represents a single frozen instant, a sudden interruption in the ongoing flow of human ambition. In the Mediterranean Sea, the water hides the galleys of ancient empires, Roman ships that once transported wine, olive oil, and marble along trade routes that connected distant civilizations. Amphorae still remain scattered across the seabed, amphorae that once held the ordinary goods of daily life. Their sweeping curves feel as recognizable as ancient pottery lifted from the soil. Yet their resting place is far removed from land. They lie in the depths where they have remained undisturbed since the moment storms or violent clashes dragged them beneath the surface. Far to the north, off the shores of Scandinavia, the ships of Viking raiders have been discovered, their wooden planks astonishingly preserved by frigid waters. These vessels, with carved prows and sails woven from wool, once tore across the seas with relentless force. Now they rest in complete darkness, silent witnesses to an era when human bravery was tied to fragile frames of timber. Every plank speaks of how far people dared to travel, guided only by the stars above and the steady pull of their oars. The sheer number of wrecks is overwhelming. Historians estimate that there may be more than 3 million still lying beneath the world's oceans. They range from the powerful warships of the Spanish Armada to merchant vessels lost in the Indian Ocean. Each one carries stories of conquest and commerce, of ambition, hope, and devastating loss. With every new expedition, divers and robotic submersibles reveal fresh discoveries. Bronze cannons, delicate porcelain bowls, coins bearing the marks of forgotten empires, and even clothing preserved in remarkable condition rise from their watery tombs. These objects are more than artifacts. They are fragments of lives once lived, moments frozen in time. It is not only ships that lie below the surface. Entire cities have been claimed by the sea. Off the coast of Greece rests Pavlopetri, the oldest known submerged city dating back more than 5,000 years. Its streets, courtyards, and building foundations remain visible, etched into the seafloor. Here people once walked, traded goods, and raised families. Rising seas and shifting earth eventually pulled the settlement under, transforming a thriving community into a concealed time capsule. Other cities have shared the same fate. Herakleion, once a great port of ancient Egypt, was swallowed by the Mediterranean more than 1,000 years ago. Divers exploring its remains have uncovered colossal statues of gods and pharaohs toppled and half buried in silt. Massive stone temples that once greeted arriving ships now stand broken and tilted, their shapes softened by layers of sand. Coins and pieces of jewelry lie scattered among the ruins, ordinary possessions abandoned in the chaos of sudden catastrophe. These underwater remains blur the boundary between legend and fact. Cities once spoken of only in myths are slowly emerging again, revealed not by poets, but by divers carrying lights and cameras. The preservation of these submerged sites is extraordinary. Sunlight never reaches the deeper ruins, and oxygen struggles to penetrate the water around them, slowing the process of decay. Fabric, scrolls, and even food have been found intact inside sealed containers. Every descent is an encounter with a forgotten world, as though the ocean itself has been holding its breath for centuries, waiting for humanity to return. The ocean's lost history reminds us that the sea is not merely a realm of unknown creatures. It is also a vast archive of human memory. Every wreck, every drowned street, and every recovered object forms a page in a book so immense it can never truly be finished. Yet with each dive, another fragment is brought back into the light, another story retrieved from silence. And as we study these traces of ourselves, the ocean continues to guard secrets, still deeper secrets that drift far beyond the reach of recorded history, hidden within the black labyrinths beneath the waves. The surface of the ocean feels immense yet familiar. Waves break, tides shift, and ships cross it with ease. But below, concealed in shadow, lie places that cause even the most experienced explorers to hesitate. Among the most dangerous and least understood are submarine caves, vast networks carved into solid rock by water over millions of years. These concealed corridors twist and wind, forming dark mazes that extend beneath coastlines, coral reefs, and continental shelves. Unlike open water, where escape may still be possible, a cave offers no mercy. Once inside, there is only a single route back, and that path is often more perilous than the journey inward. Divers who have entered these flooded caverns describe them as unlike anything else on Earth. When a beam of light sweeps across the walls, it reveals formations shaped over immense spans of time. Stalactites hang from ceilings where they once formed in open air, evidence that many of these caves were dry thousands of years ago during ice ages when sea levels were far lower. As the oceans rose, the caves filled, sealing within them a preserved record of ancient climates and vanished landscapes. In some locations, the bones of extinct animals have been discovered, protected by cold, oxygen-poor water. These caves are not merely geological features. They are time capsules preserving proof of what our planet once was. Yet their beauty is inseparable from danger. Many consider submarine caves to be more hazardous than spacewalks. In space, an astronaut is secured by a tether, supported by constant communication, and surrounded by the open view of the stars. Inside a cave, a diver relies on a single guideline leading outward, while the walls close in amid crushing silence. The margin for error is razor thin. The risk is immense. Equipment malfunctions or a single mistaken turn can mean death. There is no surface to break through for air, only solid rock and cold water extending without end. Many divers have lost their lives in these environments, and their stories circulate through the diving community as stark warnings about the merciless character of the Black Labyrinth. Charting places like this is almost impossible. Unlike the open ocean, which can be surveyed with sonar or satellites, these caves offer no simple structure or predictable shape. Some corridors are so tight that only one diver can force their way through at a time. Others expand suddenly into chambers so vast they resemble underwater cathedrals with ceilings that vanish into total darkness. Deeper still, certain passages end suddenly against blank stone, while others drop straight down into vertical shafts with no visible bottom. The intricacy of these networks means that no two cave systems are ever identical, and many remain completely unexplored and unmapped. To survive, explorers depend on reels of guideline to trace a route back, a delicate lifeline against an immense winding maze. In places such as the Yucatan Peninsula, underwater cave systems, known as cenotes, extend for hundreds of kilometers beneath the limestone bedrock. Within them, divers have uncovered human remains from ancient cultures, offerings placed there as part of sacred ceremonies. These finds remind us that caves are not just geological wonders, but also landscapes woven into human history, belief, and myth. Elsewhere in the world, including the Bahamas, enormous blue holes plunge straight downward, their depths hiding toxic layers of water where life can barely persist. Every cave system carries its own story, and each presents a unique challenge to comprehend. Science has only just begun to skim the surface of what these hidden realms contain. Inside them live strange creatures, blind fish, ghostly pale shrimp, and translucent eels, all adapted to existence without sunlight. Some species exist nowhere else on Earth. In these perpetual shadows, evolution has taken singular paths, producing life forms that demonstrate just how resilient and inventive biology can be when confronted with extreme and seemingly impossible conditions. Exploring submarine caves is like stepping into the planet's hidden lungs. They breathe in silence, guarding secrets that reach back into prehistory, and they allow only fleeting glimpses before asserting their danger. Even with modern technology, rebreathers, and powerful lights, these caves remain domains of uncertainty. They are the sea's black labyrinths, harsh, beautiful, and almost impossible to fully know. Each corridor is a reminder of how little of this planet we have truly witnessed beneath the rolling waves. In regions where sunlight never penetrates live creatures that seem as though they were imagined in the fevered dreams of myth. Yet they are neither legends nor the inventions of storytellers, but real animals shaped by evolution in ways so extraordinary they often defy belief. In the twilight zones and the abyssal depths of the ocean, life has followed routes utterly unlike those of shallow waters or the familiar animals of land. These beings show us that the rules of survival can be stretched and reshaped into forms that feel both alien and strangely elegant. Among the most unsettling of these creatures is the goblin shark, sometimes described as a living fossil, because its lineage reaches back tens of millions of years. With its long, flattened snout and a jaw that can suddenly thrust forward like a spring-loaded trap, it looks unlike any other shark on Earth. Its teeth, thin and nail-like, are designed to seize slippery prey in darkness. In photographs, its pinkish skin and vacant, ghostly eyes give it an unreal appearance, as though it belongs more to a nightmare than to the sea itself. Yet it is a quiet hunter gliding through the shadows at depths far too dark for human vision, perfectly engineered for a world where stealth and surprise determine survival. Deeper still drifts the vampire squid, a name that sounds born of horror, though in reality it is a gentle scavenger. It feeds not on blood, but on falling marine snow, the steady rain of organic material sinking from above. Its body is wrapped in a cloak-like web stretched between its arms, and when threatened, it can invert itself, revealing spiny filaments that appear far more menacing than they truly are. Its skin emits bioluminescence, tiny points of light that shimmer like stars in the abyss. Rather than being a monster of the deep, the vampire squid is a masterpiece of efficiency, adapted to survive in regions with so little oxygen that most animals would suffocate. Then there is the anglerfish, one of the deep ocean's most recognizable predators. The female bears a lantern, a glowing lure that hangs before her mouth and tempts prey into her reach. Her teeth curve inward like hooks, ensuring that once something enters, escape is impossible. In the crushing darkness of the abyss, she waits without movement, a solitary light suspended in the void, until an unwary fish drifts too close. Perhaps even stranger is her reproductive strategy. Males are minuscule when measured against females, so diminutive that they appear almost like a separate species. When a male eventually encounters a female, he attaches himself to her body, gradually merging with her until his organs waste away, and he is reduced to little more than a permanent source of sperm fused to her flesh. This extraordinary system guarantees that in the immense emptiness of the deep ocean, where meetings are exceedingly rare, reproduction can still occur. These creatures are only a handful of the ocean's most otherworldly residents, and yet they barely hint at what is possible. In the darkness at depths where pressures would instantly crush human-built submarines, evolution has composed innumerable other narratives. Some fish possess transparent heads, allowing their eyes to look straight upward, watching for the faint outlines of prey above them. Others have mouths that can gape wider than their entire bodies, enabling them to engulf prey larger than themselves in a single sudden motion. There are organisms with bodies so soft and gelatinous that they simply collapse when brought to the surface. There are beings that cannot even be examined outside their native depths because the precise combination of pressure and temperature that sustains them cannot be duplicated in any laboratory. Every remotely operated vehicle that descends into the abyss seems to encounter something previously unknown. At times, it is a newly identified jellyfish drifting through the darkness with luminous colors that glow like stained glass. At other times, it is a worm that shines in rippling patterns of blue and green. Each finding serves as a reminder that the ocean vast and secretive harbors forms of life we have barely begun to conceive. For every goblin shark or anglerfish we recognize, there may be dozens more concealed within trenches, ridges, and unexplored canyons. The most surprising aspect is that these animals, as alien as they appear, are not monsters. They are not mistakes. They are solutions. Each one embodies an answer to the same essential question: how do you endure in a realm without light, where food is scarce and where the environment seems intent on crushing you at every moment? The adaptations they display are not mere oddities. They are designs for survival. Proof that life is not limited to narrow constraints. It adapts it, transforms it, invents entirely new modes of existence. As scientists continue to gaze into these black waters, every new image and every fresh sample pushes the limits of what we believed possible. The inhabitants of the abyss are not only wonders of biology, they are clues to what might exist elsewhere in the cosmos. If such strangeness can flourish here on our own world, then the prospects for life in other concealed oceans beneath the ice of distant moons become far more plausible. Far below the shifting surface waves where the seafloor extends for thousands of miles lie enigmas that science has yet to solve. The ocean is expansive enough to consume continents, and deep enough to conceal worlds within worlds, and within that immensity, it safeguards secrets that elude even our most advanced tools. Sonar emits pulses that rebound from the seabed, charting the unseen, yet sometimes those echoes return with forms and signals that resist explanation. Unusual contacts appear on screens too large to dismiss as whales too irregular to be simple geological formations, and yet when ships or remotely operated vehicles are dispatched to investigate, the signals disappear as if whatever produced them simply melted back into the water. For decades, scientists and naval crews alike have recorded these anomalies, classified them, and struggled to interpret their meaning. Some may be echoes distorted by layers of temperature in the water. Others may reflect movements of little-known species, but many remain unresolved, their true origins concealed in the deep silence. The ocean has always been a place where things vanish. Vessels made of steel and guided by satellites still disappear without a trace, their last reported positions swallowed by storms or currents. Some may be destroyed by rogue waves, towering walls of water that rise without warning and leave no witnesses behind. Others may be dragged down by hidden reefs or seafloor ridges that are only partially mapped. And then there are the cases in which no explanation is ever discovered, where ships vanish on calm days with no distress signals transmitted. The ocean offers little evidence, dispersing wreckage across vast distances or burying it beneath sediment in a matter of hours. Even in an era of global surveillance, mysteries endure, reminding us that this immense water-covered planet has not been fully mastered by technology. Beneath the waves lie not only lost ships, but landscapes that challenge our understanding of Earth itself. On the ocean floor, spread across thousands of miles, rise structures that resemble immense geometric ridges, spirals or concentric patterns carved into rock. Some may be the result of ancient volcanic activity frozen into shapes we scarcely recognize. Others may be formed from minerals accumulating in ways unfamiliar to the world above. At times, particularly in cases such as the Baltic Sea anomaly or other unusual sonar readings, the forms detected seem overly uniform, almost unnervingly exact, as if they were shaped with intention rather than produced by random natural processes. Oceanographers remain careful in their interpretations, fully aware of how readily sonar data can be misleading and how frequently underwater terrain can trick the eye into seeing unfamiliar shapes. Even so, every newly recorded anomaly sustains the idea that the ocean floor still contains geological formations whose origins lie beyond our present understanding. There are also the mysterious sounds that pass through hydrophones captured in recordings, yet never conclusively identified. Deep, lingering rumbles that persist for minutes, pulses that propagate across entire oceans, and clicks or calls that align with no known species have all been documented. Some of these acoustic signals may be connected to sonar anomalies. Others could be related to the movement of tectonic plates or the activity of underwater volcanoes. Still, in many instances, no definitive explanation has ever been established. Scientists archive these phenomena under names such as the Bloop or Julia Small, reminders of how much of the ocean's acoustic environment remains unexplored and unexplained. Even in regions where human exploration has reached its deepest limits, such as the Mariana Trench discoveries, tend to generate more questions than answers. Unexpected ridges rise from the seabed, sediments move like rivers along the ocean floor, and bioluminescent organisms briefly glow in the beam of cameras before disappearing once more into darkness. For every insight gained through exploration, numerous new mysteries appear, each one widening the distance between what we understand and what we merely suspect. The ocean is not only the birthplace of life, but also an immense and restless archive of unresolved enigmas. Sonar contacts that suddenly vanish, ships that slip quietly into oblivion, geological structures that appear almost alien, and sounds that resonate without an identifiable source, all serve as reminders that vast regions of our planet remain governed by mystery. The next phase of discovery lies not solely in unraveling these puzzles, but also in recognizing that the ocean will forever guard some of its secrets, even as we continue to venture deeper. Despite the remarkable achievements of modern science, despite the rockets launched into orbit and the probes sent toward the farthest reaches of the solar system, our capacity to explore the ocean remains strikingly constrained. The technology at our disposal, impressive as it may be, is constantly challenged by the sheer scale pressure and hostility of the deep sea. Even the most advanced machines struggle against crushing depths, immense distances, and an environment that offers little margin for error. Human-occupied submersibles stand among the most recognizable tools used to reach the depths. They are extraordinary feats of engineering, capsule-shaped and encased in steel or titanium walls thicker than those protecting our most valuable treasures. However, this strength comes with significant limitations. Every descent is costly, demanding extensive preparation, specialized personnel, and support ships to deploy them. A single dive may last only a few hours, despite months or even years of planning beforehand. These submersibles can descend only a limited number of times before requiring major maintenance, and only a small number worldwide are capable of reaching the deepest trenches. As a result, direct human exploration of the ocean is rare, a pursuit reserved for a handful of dedicated scientists or the occasional adventurer willing to accept extreme risk for a brief glimpse into the abyss. To push beyond these limits, remotely operated vehicles or ROVs are often deployed where people cannot safely go. They drift through darkness, connected to surface ships by thick cables that supply power and communication. Their cameras reveal eerie landscapes never previously observed, and their mechanical arms collect samples from vents and trenches. Yet they too are vulnerable, constantly threatened by the very conditions they are designed to endure. Cables can fail under strain, components can be crushed or clogged by sediment, and intense pressure can deform even carefully engineered housings. Each ROV is expensive to construct and operate, and many have been lost to the depths, disappearing into regions from which recovery is impossible. Their operational time is limited, their missions brief, leaving much of the ocean still largely unexplored. Satellites, which have transformed our understanding of space, encounter an insurmountable barrier when faced with water. They can outline continents, monitor currents, and detect subtle variations in sea surface height that suggest mountains and trenches far below. Yet they cannot penetrate the depths themselves. Light and radio waves scatter and fade within just a few meters of water, rendering the vast interior of the ocean invisible to their instruments. At best, satellites provide vague shadows and blurred hints of what lies beneath, never the sharp detail they deliver when observing distant planets and stars. This limitation makes the contrast between ocean exploration and space exploration even more striking. Telescopes can gaze across billions of light years, producing detailed images of galaxies that existed long before Earth formed, while sonar, our primary means of studying the seafloor, struggles to clearly probe more than a few kilometers into the deep. The further we attempt to peer into it, the less sharply defined it becomes. Creating a detailed map of the ocean would require centuries using today's technology, and even if that effort were possible, the constantly changing nature of the sea would ensure that no map could ever remain fully accurate. The sheer scale of the ocean is its strongest shield against our efforts to truly comprehend it. Every tool we deploy, from crude submarines to ROVs to orbiting satellites, runs into physical and technical limits that make the idea of completely exploring the sea feel almost unattainable. At present, what we possess is only a scattered collection of pieces. Occasional descents into deep trenches, brief observations made by delicate robotic explorers in distinct shapes traced by satellites high overhead. Each fragment contributes something, yet the full image will forever be unfinished. In this way, the ocean preserves its secrets not solely because it is immense and unforgiving, but because even our most advanced machines are still too small to match the scale of its vastness. The sea serves as a reminder that although we may stretch our ambitions toward the stars, we remain humbled by the depths of our own planet. The ocean is not merely deep and enigmatic. It is vast beyond easy understanding. When scientists describe its magnitude, the figures themselves feel almost unreal. The volume of Earth's oceans is estimated at more than 350 quintillion gallons of water, a quantity so enormous that it exceeds what the human mind can easily grasp. To put this into perspective, if every person alive today attempted to count each gallon individually without sleeping and without stopping for a single second, the process would take longer than the entirety of recorded history. The sea is not simply wide. Its immensity is beyond measurement. A body of water so immense that our efforts to fully explore it seem nearly absurd when set against its true scale. Exploration depends on instruments, yet those instruments must function within strict boundaries of time and energy. Sonar systems can sweep the seafloor, sending sound waves downward and receiving echoes that trace the outlines of ridges and trenches, but each pass reveals only a tiny portion of the whole. Ships dragging sonar arrays inch slowly across the ocean's surface, their signals penetrating the depths to assemble a partial picture of what lies below. If we attempted to scan every region of the ocean in this manner, working continuously without interruption, the task would still take many thousands of years. And by the time the final section was charted, the earliest maps would already be obsolete as shifting currents move sediments underwater, volcanoes alter ridges, and new fractures open within the planet's restless crust. Even satellites, which provide us with wide-ranging views of the ocean's form, cannot escape the problem of scale. They can measure subtle variations in the height of the sea's surface, revealing the gravitational influence of seamounts and deep trenches far beneath. But those details remain indistinct, like shapes glimpsed through thick fog. Turning those vague impressions into precise images demands close observation, and close observation consumes time. A single research expedition might return with remarkable findings. Yet when considered against the backdrop of the entire ocean, it is comparable to examining a single raindrop in an effort to understand an entire storm. This vastness affects not only mapping, but discovery itself. Each remotely operated vehicle that descends into the darkness explores only a narrow cone of space, a slender slice of the abyss. Even if thousands of such dives were conducted, they would barely begin to touch the surface of the deep. Every time a new species is recorded, or an unfamiliar landscape appears on camera, it comes with the awareness that countless more remain unseen, concealed within an endless expanse that has never encountered light or lens. The ocean is never still. Its waters move in cycles that can span centuries as currents twist and interlace, transporting heat, nutrients, and living organisms across entire ocean basins. A gallon of seawater taken from the surface may not return to that same location for hundreds of years as it travels through this vast global circulation system. Over such timescales, conditions shift, species adapt or disappear, and the seafloor itself changes shape. Exploration thus becomes a challenge not only of distance but of time, as the subject of study continues to evolve before it can ever be fully understood. Calling the task mathematically impossible is no exaggeration. Imagine fleets of scanning vessels, each one transmitting sonar signals day and night. Imagine armadas of robotic submarines roaming every depth. Even then, the immense volume of water would overwhelm them, a reminder that the ocean is not a controlled laboratory that can be neatly indexed, but a living system so vast that its secrets will always move beyond our grasp. Perhaps this is part of the ocean's lasting power. Its scale guarantees that it will never be completely known. It allows mystery to persist in a world where so much else has been measured, charted, and classified. Even as our machines become ever more capable, the fundamental numbers do not change, and the ocean continues to teach us that some frontiers are simply too large to be conquered. When we consider how humanity allocates its resources, the imbalance is striking. Every year, billions upon billions of dollars are devoted to the exploration of space. Rockets rise into the sky carrying cameras and instruments, satellites are deployed in vast constellations, and ambitious plans are laid for Mars and beyond. By comparison, the oceans, which cover more than 70% of our planet and contain the greatest share of its unknowns, receive only a fraction of that attention. Funding is limited, research vessels are few, and scientists who dedicate their lives to studying the sea often struggle simply to secure enough support for a single expedition. This gap does not reflect a lack of importance. The oceans regulate Earth's climate, sustain billions of people with food, and hold immense potential for medicines, minerals, and energy resources. Yet in political and public imagination, the seafloor lacks the allure of the skies above. Space has long been wrapped in a sense of spectacle, carrying the allure of undiscovered worlds and imagined civilizations, a powerful symbol of humanity, pushing beyond its birthplace. The ocean, although just as foreign and enigmatic, stays concealed in darkness and quiet, largely unseen by those who hold power and make decisions. It lacks the visual drama of a rocket lifting off, and as a result, the drive to investigate it feels far less pressing. Marine science is frequently confined to rare and narrow chances. Research teams may wait many years for an opportunity to send a vessel to sea, and when that moment finally arrives, every single hour becomes precious. Expeditions must be planned with extreme care because budgets seldom permit multiple trips. The equipment involved is costly to keep operational, and if a device fails under the immense pressure of the depths, it may be lost forever. Even creating specialized submersibles or remotely operated vehicles often depends on private benefactors or partnerships with industries like oil and gas sectors that pursue exploration for their own priorities. This reliance often means that pure scientific inquiry is pushed aside in favor of economic usefulness. The disparity becomes even clearer when scale is taken into account. Space agencies operate with enormous infrastructures, large teams of engineers, and consistent funding streams that support continuous progress. Oceanography, in contrast, often relies on aging fleets, instruments assembled from scarce resources, and scientists who spend as much time applying for grants as they do actually conducting research. The promise is immense, yet the resources needed to fully realize it remain frustratingly out of reach. This is particularly ironic because discoveries from the deep sea could affect daily life almost immediately. Microorganisms living around undersea vents may provide breakthroughs for new antibiotics. A deeper understanding of fish populations could help manage them sustainably, protecting food supplies for future generations. Precisely charted ocean currents could improve climate models and sharpen forecasts of storms and droughts. Without sufficient investment, however, such knowledge arrives slowly and in fragments, leaving society less prepared for changes already underway. Some scientists speak of a blue space race, a future where ocean exploration is treated with the same urgency as space exploration. But this vision remains distant. Governments hesitate, investors prefer faster profits, and much of the public remains unaware of how much remains unknown beneath the waves. The sea continues to wait as it has for millions of years, while attention drifts elsewhere. And so the pattern persists. Rockets rise dramatically into the sky, while research vessels pass unnoticed telescopes, study distant galaxies while sonar struggles to chart trenches only a few miles offshore. This imbalance does not reflect a difference in importance, but rather where human imagination chooses to roam. This lack of focus ensures that vast portions of the ocean remain unexplored, not because they are inaccessible, but because the determination to explore them has never matched their true worth. Each attempt to descend into the deep places humanity in an environment that actively resists intrusion. The ocean is not passive. It pushes back with forces that test both the human body and engineered machines. It is a domain where every shift in temperature, every ton of pressure, and every mile of depth increases the danger. Exploration is not merely curiosity, it is a gamble, and every descent carries the weight of that risk. Cold is among the earliest and most persistent threats. As depth increases, the warmth of the sunlit surface is left behind. Temperatures drop steadily until they linger just above freezing, a cold so intense it penetrates steel and titanium, challenging even the best insulation. For human divers, even when protected by advanced suits, such cold can cause numbness and exhaustion. For machines, it slows battery chemistry, thickens lubricants, and makes materials more fragile. The deep ocean does not need to strike aggressively. Its cold alone can weaken and destroy what enters it. Pressure is an even harsher opponent. With every 10 meters of descent, the mass of water overhead grows heavier. By the time a vessel reaches 1,000 meters, the force pressing against it is already 100 times greater than at the surface. In the deepest trenches, that pressure increases more than 1,000-fold. To withstand it, submarines must be constructed like fortresses, with walls thicker than bank vaults and rounded forms that spread stress evenly. Even so, the margin for error is incredibly small. A crack no wider than a hair can trigger a catastrophic collapse. Machines, no matter how robust, carry this ever-present risk, and for humans sealed inside them, the awareness of it never truly fades. Isolation intensifies the danger. Once an expedition departs the surface, it enters a realm where communication becomes slow and limited. Radio waves cannot travel through water, so the instant connections that guide astronauts or pilots disappear. Messages must move as sound through the sea, delayed and distorted, or along long cables, linking delicate vehicles to ships above. If something fails, help cannot arrive quickly. A stranded diver, or disabled machine, is isolated far below, beyond the immediate reach of rescue. This sense of separation is a key reason each descent feels so stark and sobering. Those who venture downward understand that the sea offers no second chances. For divers in particular, the dangers are intensified by biology. Human lungs were never designed to withstand extreme pressure, and our tissues react in uncertain ways when gases are compressed. Excess nitrogen can impair the brain, causing disorientation and faulty decision-making. Oxygen, when present at high levels, can also become poisonous. Even the return to the surface carries risk, because ascending too rapidly allows gases to expand inside the body, forming bubbles that can maim or prove fatal. Advanced methods and specialized gear push the boundaries of what the human body can tolerate, but those boundaries are still very tight. Most of the deep ocean remains completely beyond our physical reach. Machines are built to extend those limits, yet they fail as well. Cables snag and propellers clog with sediment, cameras fracture under crushing pressure, and electronic systems deteriorate in corrosive salt water. At times, entire submersibles are lost, slipping quietly into the depths with no hope of recovery. Every expedition holds the possibility of loss, whether it involves costly equipment, irreplaceable data, or in rare and heartbreaking instances, human life. Still, explorers return to the ocean time and again, compelled by the allure of the unknown. The dangers never disappear, but each successful dive offers a fleeting view of what lies hidden in the darkness. Cold, immense pressure and isolation make the deep sea an unforgiving frontier, yet they also make it profoundly humbling, reminding us that discovery often occurs at the very edge of human endurance. The ocean does far more than simply blanket the surface of our world. In many respects, it functions as a memory, an archive preserved not in libraries or digital files, but in the silent accumulation of sediments drifting slowly downward. Every grain of sand, every speck of dust, every shell from a microscopic organism that falls through the water ultimately settles on the ocean floor. Over immense spans of time, these fragments are compressed into delicate layers, stacked one atop another, forming pages in an enormous geological journal. Within these strata rests the narrative of Earth itself, records of changing climates, mass extinctions, species that thrived and disappeared, and the forces that have molded the planet across millions of years. When researchers extract core samples from the depths, they are essentially retrieving time capsules. A single column of mud can contain hundreds of thousands of years of history, with each centimeter marking centuries of transformation. Inside those thin bands of sediment preserved in chemical signatures and microscopic fossils are hints about past temperatures, patterns of rainfall, and even the makeup of the atmosphere when the material settled. Some layers reveal unmistakable evidence of catastrophe, such as sharp spikes of iridium that signal the asteroid impact which ended the age of the dinosaurs. Other layers show slow, rhythmic shifts linked to ice ages recorded in the shells of plankton that mirror the chemistry of the oceans they once inhabited. Yet gaining access to this memory is anything but simple. The deep sea floor is not a neat shelf waiting to be read. It is a sensitive environment, fragile and easily disrupted. The mere act of lowering instruments can stir sediments, wiping away the fine details scientists hope to study. Vehicles that touch down can crush ecosystems whose inhabitants have lived undisturbed for centuries. Even careful drilling carries the risk of blending layers together, obscuring the orderly sequence that nature composed so patiently over eons. The challenge lies not only in reaching the bottom, but in doing so without damaging the record preserved there. This difficulty is magnified by the sheer scale of the ocean archives. Sediments are far from uniform. They vary with depth, proximity to land, and the shifting paths of ocean currents. One core sample may recount a volcanic eruption that darkened skies thousands of years ago, while another taken a few hundred miles away might document the slow buildup of nutrients that fueled bursts of life. Constructing a global understanding demands countless samples collected from scattered locations across a seafloor that spans more than 200 million square miles. The puzzle is so vast that even the most committed teams can assemble only pieces of it. Within those pieces, however, lie remarkable revelations. Deep sediment layers have exposed cycles of warming and cooling long before humans existed, demonstrating how finely balanced Earth's climate has always been. Other deposits preserve signs of ancient tsunamis, their immense power frozen in sudden layers of sand carried far from shore. In some regions, sediments contain the remains of organisms so tiny they are visible only under a microscope. Yet within their shells and chemical fingerprints is information about oceans that existed tens of millions of years in the past. These records reach further back through time than any document created by humans, extending beyond the earliest cave paintings or clay tablets, and they offer glimpses into a world we have never directly witnessed. While these archives are invaluable to science, they are also fragile. Human activity from deep-sea trawling to seabed mining threatens to disrupt sediments on a scale never experienced before. What took millions of years to accumulate and preserve can be wiped away in moments by heavy machinery dragged across the ocean floor. This danger hangs over modern exploration, raising difficult questions about how much of the ocean's memory might vanish before we have even learned how to read it. And yet the ocean continues to write its story day after day. Dust carried on the wind settles gently into the depths. Ash from distant volcanic eruptions drifts downward. Shells sink slowly and the remains of living creatures fall to join the growing archive. Layer after layer forms, building a living memory that deepens with every passing century. It waits in silence, patient and immense, safeguarding the story of Earth in ways we are only beginning to comprehend, even as we move forward into the next chapter of discovery. For as long as people have looked out across the sea, there has been a powerful desire to know what lies beneath its surface. The ocean has always been a realm of imagination filled with fear as well as wonder. Yet for most of human history, it remained an unreachable frontier. The notion of traveling to its greatest depths seemed as unrealistic as reaching the stars. But in the 20th century, daring efforts were made to overcome that barrier, to send humans into the abyss and uncover the secrets hidden there. One of the earliest and most legendary of these attempts took place in 1960, when a vessel known as the Trieste descended into the Mariana Trench. This trench, concealed in the western Pacific Ocean, is the deepest known location on Earth, and the Trieste carried 2 men all the way to its floor. The craft was not streamlined like a conventional submarine. Instead, it was shaped like a bathyscaphe, a rounded, bulky chamber, designed to endure the crushing pressure of the deep sea. Its walls were so thick and heavy that it could only descend slowly, sinking through the water column for hours before finally reaching the bottom. When it touched the seafloor, nearly 11 kilometers beneath the surface, the men inside looked through a small viewing window and saw a landscape no human had ever seen before. They remained only briefly before beginning the long ascent back toward the light, but their journey marked a profound turning point. Humanity had reached, however momentarily, the deepest frontier of the planet. Yet this achievement did not unleash an era of routine exploration. In the decades that followed, very few people returned to such depths. The reason was straightforward. The cost and complexity were immense. Constructing a vehicle capable of surviving such pressure posed extraordinary engineering challenges. Deploying and supporting it demanded ship's crews and flawless coordination, while the risk of failure was ever present. The deep ocean offered nothing easily, and the Trieste's descent remained unmatched for more than 50 years. It was only in the early 21st century that another human made the journey alone. In 2012, filmmaker and explorer James Cameron piloted his custom-built submersible down to the Challenger Deep, the same trench floor first reached in 1960. His vessel, named the Deep-Sea Challenger, was a tall, slender machine packed with lights and cameras. Unlike the Trieste, which had limited ability to record what it encountered, Cameron's craft was designed to capture detailed images and collect samples. He spent several hours exploring the seafloor before ascending once more, offering the first modern view of the deepest part of the world's oceans. The accomplishment drew global attention not only because of the feat itself, but also because it had taken more than half a century for anyone to return. Between these milestones and in the years since, only a small number of missions have reached full ocean depth. Each has revealed new insights into the life that exists in those dark trenches, yet each has also underscored how restricted our access still is. The pressure at such depths is so extreme that every dive carries the risk of catastrophic failure. Even the most carefully designed machines must undergo repeated testing, pushed to their limits, before being trusted with human lives. A single expedition can cost millions of dollars, and the knowledge gained, while significant, represents only a tiny fraction of what remains concealed. The truth is that despite centuries of seafaring, and despite the era of satellites and space travel, fewer people have visited the bottom of the ocean than have walked on the surface of the moon. The small group of explorers who have descended so far stand as symbols of human determination, but they also reveal the boundaries that technology, cost, and resources continue to impose upon us. Each expedition reveals not just human cleverness, but also the overwhelming scale of what lies before us. What has already been accomplished is remarkable, and yet when compared with the immensity of the oceans, it serves as a quiet reminder that we have barely brushed the boundary of a domain that may never be entirely known. When discussions turn to the future of ocean exploration, they are often marked by a blend of optimism and uncertainty. On one hand, there is faith in emerging technologies that might carry us deeper and farther than at any point in history. On the other, there is the sobering awareness that the obstacles of the deep have consistently exceeded our aspirations. The sea has endured for millions of years, and it remains an open question whether the next generation of human-made machines will truly reveal its hidden truths or merely glide over the surface of its enduring mystery. Among the most frequently discussed concepts are autonomous submarines directed by artificial intelligence. Unlike vessels operated by human crews, these machines could travel for weeks or even months without pause, descending into trenches and inching along the seafloor in regions far too hazardous for people. They would not grow exhausted, they would not succumb to fear, and they would not demand constant oversight. Entire swarms could be released, moving like shoals of mechanical fish, each equipped with cameras and sensors, exchanging data with one another and charting expanses that no single ship could ever hope to cover. In principle, this approach could make the ocean's seemingly unmanageable size more approachable, dividing it into segments small enough to examine. Yet even the most sophisticated robots remain subject to the harsh realities of the environment they enter. Power supplies deplete rapidly in frigid conditions, and sensitive electronics slowly decay in corrosive salt water. With every additional mile of depth comes pressure that challenges every seal and structural joint. One minor weakness in construction can spell the silent disappearance of a machine condemned to rest forever in darkness. While artificial intelligence can navigate and adjust, it cannot yet defeat the immense physical demands of the abyss. For the moment, visions of coordinated swarms and vast fleets exist more as experiments and prototypes than as everyday tools. Discussions about what lies ahead often return to the issue of funding. Pure scientific curiosity has seldom been sufficient to support large-scale ventures into the deep. Instead, many of the emerging technologies are closely linked to industries that regard the ocean primarily as a source of materials. Deep-sea mining, for instance, is promoted as a method to extract valuable minerals from the seabed resources considered essential for electronics, batteries, and renewable energy infrastructure. Corporations are channeling investment into machines capable of reaching abyssal plains, collecting nodules rich in rare metals, and transporting them to the surface for processing. Some suggest that such operations might, as a byproduct, improve our maps and knowledge of the deep, since mining activities require extensive surveys of the seafloor. However, a clear tension exists. Exploration motivated by financial gain is fundamentally different from exploration inspired by curiosity and awe. Machines built for mining are engineered to remove, not to observe, and the delicate ecosystems of the deep may be disrupted before they are properly understood. The limited insights we have into hydrothermal vents and abyssal environments indicate that they host species found nowhere else on Earth. Passing heavy machinery over these regions in search of minerals could eliminate forms of life before they are even recorded, permanently erasing chapters of Earth's history. The question remains unresolved. If the resources for exploration are tied to exploitation, can the result truly be called exploration? Some optimism lies in cooperative scientific efforts, where countries and institutions exchange information openly and collaborate toward shared goals. International initiatives that employ networks of sensors, drifting instruments, and autonomous vehicles already observe ocean currents and monitor climate-related changes. Enhancing these systems with more advanced technology could offer a more comprehensive understanding of ocean processes without placing profit above preservation. Perhaps in time, fleets of AI-driven submarines will operate not in service of industry, but for humanity as a whole, functioning as explorers whose sole mission is to map the unknown in pursuit of knowledge. Still, the sheer scale of the ocean tempers all such hopes. Even if armadas of machines traverse its depths, even if every commercial venture contributes to research along the way, the sea will remain too immense, too ever-changing, and remains far too hostile to ever be entirely mastered. The future of exploration may deliver additional glimpses, finer detail, and moments of astonishing discovery. yet the boundary of the unknown will always recede further into the distance. What lies before us is not the promise of a finished map, but the chance to understand just a little more. Whether that represents hope or illusion depends on how we choose to approach the depths, whether we see them as something to exploit or as something deserving of respect, a realm where every finding should be regarded as a delicate gift. And as we imagine what might come next, the ocean continues to wait as it always has, holding far more than any fleet of machines or web of sensors could ever uncover. There is a quiet question that lingers behind every expedition, every design for a new submarine, every dream of charting the last hidden corners of the Earth. Should we explore everything? The desire to know is profoundly human. It has carried us across deserts, over mountains, and into space. Yet the ocean presents not only a challenge of scale and technology, but also a challenge of philosophy. In the dark waters, where so much life has evolved, unseen discovery and destruction often arrive together. When we think about the unknown, it is easy to picture it as a puzzle waiting to be solved. But the ocean is not a puzzle box. It is a living, breathing system, intricate and fragile. In places untouched for millions of years, ecosystems have emerged that rely on delicate balances. The smallest disturbance, the glow of a camera, the scrape of a machine, or the removal of a single mineral deposit could disrupt those balances in ways that can never be reversed. To open every door is to risk breaking what has endured in the darkness without us. This reality creates an ethical dilemma. On one side stands curiosity, the urge to see, to understand, to push the edges of knowledge outward. On the other side stands restraint, the awareness that knowledge gained too quickly may cost more than it gives. Some scientists argue that mystery itself acts as a form of protection. By leaving certain regions of the ocean untouched, we shield them from interference, from exploitation, and from the unintended consequences of our own ambition. The question then shifts from whether we can explore to whether we should. There is also the question of perspective. Exploration is often framed as conquest, as a way of extending human presence into places that existed long before we did. Yet the ocean does not require us. It flourishes with or without our gaze. Its memory is written in layers of sediment. Its creatures adapt to crushing pressures. Its cycles continue without pause. We are the anomaly, not the rule. The belief that every corner must be opened and every secret revealed may say more about us than about the ocean itself. At the same time, choosing not to explore is not a simple decision. Curiosity is not merely a desire, it is also a tool. Understanding ocean currents helps us predict storms. Studying deep-sea microbes may lead to medicines that save lives. Discovering new species deepens our knowledge of biology. These are not trivial gains. They remind us that exploration can bring benefits as well as risks. The challenge lies in balance, in seeking knowledge without trampling the very wonders we hope to preserve. Philosophers of science sometimes speak of a right not to know. It is the idea that mystery has its own value, that there are spaces where not knowing is an act of respect. The ocean tests this idea more than almost any other frontier. If a trench conceals species that have never known light, do they gain anything from our arrival? If a cave has remained sealed for thousands of years, is breaking it open truly discovery, or is it loss dressed up as progress? These questions resist easy answers, yet they deepen our understanding of the relationship between humanity and the natural world. Perhaps the greatest lesson the ocean offers is humility. For all our satellites and submarines, we remain small against its vastness. The unknown is not an empty space waiting to be filled. It is a mirror reminding us of our limits. The choice to explore or not to explore is also a choice about what kind of species we wish to be, one that consumes every mystery until nothing remains hidden, or one that allows some secrets to endure protected in the dark. And still the pull of curiosity persists. The ocean seems to hum with it, tempting us with hints of unnamed species, unmapped landscapes, and histories yet to be uncovered. Yet perhaps its greatest gift lies not in what it reveals, but in what it keeps from us, inviting us to wonder without ownership, to respect without intrusion, and to see mystery itself as part of the story of life on Earth. For all our progress, for all the steel and circuitry lowered into the depths, the ocean still holds more mystery than any frontier we have ever confronted. We imagine mastering the oceans, mapping every trench and cataloging every form of life. Yet the seas will always be broader, deeper, and darker than we are. They are not merely a location on Earth, but a reminder of our boundaries, a quiet lesson that some marvels will forever stay beyond our grasp. It is easy to think of the ocean as familiar. We watch its surface each day rising and falling with the tides gleaming beneath the sun, and we convince ourselves that what we see is all there is. But beneath that shimmering skin exists a realm more alien than Mars, an immensity where mountains higher than Everest stand unseen, where vast currents flow like rivers carrying the memory of ancient climates, and where creatures drift in forms and colors more strange than any artist could ever imagine. Each time we venture into that darkness, we return with something new, yet every discovery only expands the boundary of what remains unknown. There is humility in this realization, and there is also comfort. The oceans remind us that Earth is still alive with secrets that even in an age of satellites and supercomputers wonder has not been depleted. The sea continues to hold stories older than humanity itself, written into layers of sediment and murmured through shifting currents. It protects species that have never known the light of day, and it conceals landscapes that human eyes may never witness. It is at once a cradle of life and an immense abyss, both a provider of sustenance and a domain of profound silence. As we consider this journey through its depths, it becomes clear that exploration is not about domination, but about listening. Every ghostly sound captured by hydrophones, every brief shimmer of bioluminescent light, every fleeting glimpse of an unfamiliar creature is the ocean speaking in fragments. We can collect those fragments, arrange them into meaning, and learn from them. Yet the whole will always remain greater than anything we can fully contain. That reality is not a failure, but a gift. It means the ocean will always have more to offer, more to reveal, more to remind us of the vast scale of life and of time itself. And so, as this story of the deep reaches its pause, the ocean continues as it always has, endless and unbroken. It waits in silence, holding its memories, sheltering its inhabitants, and shaping the destiny of the world above. What lies beyond our reach may never be completely known, but it will always call to us, awakening the same blend of awe, curiosity, and humility that has drawn sailors, scientists, and dreamers for centuries. If you have felt carried along by this journey, I invite you to join me again in the future, as together we gently wander through the mysteries of science. A simple, like a quiet tap of subscribe, helps this small corner of curiosity reach others who may be searching for wonder in the stillness of their night. And if you feel inclined, share your thoughts in the comments. What do you believe lingers in the depths? Which secrets of the sea feel most haunting to you? Every voice adds to the dialogue, just as every drop contributes to the ocean. This channel has become a meeting place for dreamers scattered across the globe, each of us connected by tides of curiosity, and it is always a pleasure to see where you are listening from and at what hour of night or morning you drift into these stories. The sea will go on endless and unknowable, and we will carry its mystery with us. For though we dream of exploring every corner, of lifting every shadow, the ocean will always remain greater than our reach, deeper than our instruments, and darker than our imagination. It is, and will always be, Earth's greatest frontier.